Right now, as you read this, the sun is converting 4 million tons of matter into pure energy every single second. This has been happening for 4.6 billion years. It will continue for another 5 billion years, give or take a few hundred million. At that point, the sun will expand into a red giant star roughly 200 times its current diameter. Earth's orbit sits at 93 million miles from the sun. When the expansion completes, the sun's outer atmosphere will reach somewhere between 108 million and 150 million miles from its center. The mathematics are unforgiving. Earth will either be swallowed entirely, vaporized in the outer layers of our dying star, or it will survive as a scorched, airless rock orbiting a white dwarf corpse. Either way, every ocean will have boiled away billions of years earlier. Every mountain will have melted. Every trace of biology will have been sterilized by radiation and heat long before the final act. This is not speculation. This is stellar physics, confirmed by observations of thousands of other sun-like stars in various stages of evolution throughout our galaxy. But here is what makes this story strange. What transforms it from a distant cosmic inevitability into something that speaks to the core of what humanity is and might become. We will not be here to witness it. Not humanity as we know it, not even remotely. The timeline does not allow for it. When astronomers and planetary scientists examine the future habitability of Earth, when they run the models forward through deep time, they discover something uncomfortable. The window for complex life on this planet, for anything resembling the biosphere we inhabit now, closes far sooner than 5 billion years. It closes within the next 1 to 2 billion years at most, likely much sooner. The mechanism is prosaic, almost mundane compared to the spectacular death of the sun. It is simply that the sun is getting brighter. Stars like the sun undergo what is called main sequence evolution. They spend the vast majority of their lives in a stable state, fusing hydrogen into helium in their cores. But this stability is not static. The core gradually becomes denser as helium accumulates. This slightly increases the rate of fusion, which slightly increases the energy output, which slightly increases the brightness. The change is gradual on human timescales, essentially imperceptible across centuries or even millennia, but it accumulates. When the sun first ignited fusion 4.6 billion years ago, it was roughly 70% as bright as it is today. In 1 billion years, it will be 10% brighter than it is now. In 2 billion years, it will be 20% brighter. These percentages sound small, but the effects on planetary climate are profound and irreversible. The mechanism that dooms Earth well before the sun's red giant phase is called runaway greenhouse warming. It begins subtly. As solar radiation increases, more water evaporates from the oceans. Water vapor is a greenhouse gas, far more effective at trapping heat than carbon dioxide. More water vapor means more trapped heat, which means more evaporation, which means more water vapor. This is a positive feedback loop. At some point, the process becomes self-reinforcing and unstoppable. The oceans begin to boil. Not metaphorically, literally. Water vapor floods into the stratosphere, where ultraviolet radiation from the sun breaks it apart into hydrogen and oxygen. The hydrogen, being light, escapes into space. The oxygen reacts with surface rocks. Over hundreds of millions of years, Earth loses its water entirely. What remains is a planet like Venus, shrouded in thick carbon dioxide atmosphere, surface temperatures exceeding 400 degrees Celsius, all life extinguished. The timeline for this transition remains debated among climate scientists and astrobiologists, but the range is sobering. Conservative estimates suggest Earth remains habitable for complex life for another 1 to 1.5 billion years. More pessimistic models, accounting for factors like declining carbon dioxide levels as silicate weathering accelerates with warming, suggest the window could close in as little as 500 million to 800 million years. Some researchers argue that the fossil record itself provides evidence for this process already underway. The long-term trend in Earth's climate, when you average out ice ages and warm periods over hundreds of millions of years, is toward a hotter planet. The sun's gradual brightening is not some future threat. It is happening now, has been happening since the first bacteria emerged, and will continue until Earth becomes uninhabitable. Think about that for a moment. 500 million years sounds like an unimaginable span of time. It is longer than complex multicellular life has existed on Earth. 500 million years ago, the Cambrian explosion was just beginning. There were no plants on land, no insects, no vertebrates, nothing with a backbone. In the 500 million years since then, life conquered land, evolved flight, developed intelligence, built civilizations. 500 million years seems infinite from a human perspective. But it is finite. It has an end. And when that end arrives, when the runaway greenhouse begins, nothing we recognize as life will survive on Earth's surface. Now consider what humanity might look like if it persists for even a tiny fraction of that time. Modern humans, Homo sapiens, emerged roughly 300,000 years ago. Civilization, depending on how you define it, is perhaps 10,000 years old. Industrial civilization is less than 300 years old. If humanity survives for just 1 million more years, that would represent more than 3 times our entire evolutionary history as a species. 1 million years is a blink compared to 500 million. Yet, it is enough time for unimaginable change. Evolution, technology, culture, everything we think defines humanity would be unrecognizable. The beings that might exist 1 million years from now, assuming they descend from us in any meaningful sense, would be as alien to us as we are to early Homo erectus. They might not live on planets. They might not be biological. They might not think in ways we would recognize as thought. Scale it further. Imagine humanity's descendants, whatever form they take, persist for 10 million years. That is roughly how long a typical mammalian species lasts before evolving into something else or going extinct. In 10 million years, the continents will have moved noticeably. Mountain ranges will have risen and eroded. New ocean basins will have formed. The climate will have cycled through multiple ice ages and warm periods driven by orbital variations, though the underlying trend toward increasing solar radiation will be steadily advancing. Any technological civilization lasting 10 million years would have engineering capabilities beyond our comprehension. They could potentially move planets, harness the full energy output of the sun, spread throughout the galaxy. They would face challenges we cannot imagine, but they would still be bound by physics, still subject to entropy, still operating under the constraint that their home star is slowly but inevitably brightening toward a lethal intensity. The research confirming Earth's finite habitability window emerged gradually from multiple fields over the past few decades. In 1988, James Casting, then at Pennsylvania State University, published some of the first detailed calculations of the runaway greenhouse effect on Earth, as applied to the distant future. His models suggested Earth would lose its oceans to space in about 1 billion years. Subsequent work refined these estimates, incorporating better understanding of atmospheric chemistry, cloud feedback effects, and the carbonate-silicate cycle that regulates carbon dioxide levels. In 2011, a team led by Ravi Kopparapu at Penn State revisited the habitable zone calculations for exoplanets, which implicitly define when Earth exits its own habitable zone. Their models suggested the runaway greenhouse threshold for Earth might arrive sooner than previously thought, within 800 million to 1 billion years. More recent studies have examined specific mechanisms that could accelerate the process, like the decline in atmospheric carbon dioxide as the sun brightens, which paradoxically makes Earth more vulnerable to greenhouse warming by reducing the efficiency of silicate weathering. Before you drift off tonight, take a moment to ground yourself in the present and leave a comment. What time is it where you are right now, and where in the world are you watching from? What makes this timeline particularly poignant is the contrast with what humanity worries about in the present. We measure our concerns in decades, maybe centuries if we are being ambitious. Climate change, resource depletion, political instability, these operate on timescales of years to generations. The idea of planning for events a billion years away seems absurd, almost comical. Yet the physics is indifferent to our time horizons. The sun will continue its evolution whether we think about it or not. Earth's habitability will end whether we prepare or not. The question is not whether this future arrives, but whether anything we would recognize as our legacy exists when it does. This raises uncomfortable questions about meaning and purpose. If humanity's ultimate fate is extinction, if Earth itself becomes a dead world, what does anything we do matter? This is an old philosophical problem, but the specific timeline of Earth's future gives it a particular sharpness. We know roughly when the stage itself will cease to exist. We can calculate within reasonable margins when the last possible moment for biology on this planet will occur. Everything we build, everything we discover, everything we create must either escape Earth or end with it. There is no third option. The universe does not provide us with indefinite time to figure things out. Yet this same knowledge also provides a strange kind of clarity. If we know Earth's habitability is finite, if we can calculate approximately when that finitude becomes acute, then we also know that any long-term survival of our lineage requires becoming an interplanetary, then interstellar species. This is not optional for survival beyond a certain timescale. It is mandatory. The technological development necessary for this transition, the social and cultural evolution required to sustain civilizations across such spans of time and space, these become not merely aspirational but necessary conditions for existence beyond the next few 100 million years. In a sense, the sun's slow brightening and the eventual red giant phase far beyond that serve as a kind of cosmic deadline. Solve the problems of space travel, energy, resources, social coordination at scale, or accept extinction. The universe does not compromise. And so the title's assertion becomes clear. The sun will swallow Earth in 5 billion years, but humanity is already gone. Not because we will destroy ourselves necessarily, though that remains possible. Not because some external threat will eliminate us, though that too is possible. But because 5 billion years is so incomprehensibly long that nothing recognizable as human civilization, as human biology, as human consciousness could possibly persist unchanged across it. If anything of us remains, it will be so transformed by time, evolution, technology, and adaptation to environments we cannot imagine that calling it human would be a courtesy at best. We are already gone in the sense that our present form, our present concerns, our present way of being cannot and will not survive into the deep future. What might survive? What might carry some fragment of our lineage forward? That is the question that makes this story worth contemplating as you drift toward sleep. The sun's evolution toward red giant status represents one of the most thoroughly understood processes in astrophysics. We can observe thousands of stars in various stages of this evolution. We know the physics of stellar interiors with extraordinary precision. The uncertainty in when Earth becomes uninhabitable is not about whether it will happen, but about the specific mechanisms and timelines of atmospheric loss and surface sterilization. These are details that matter immensely for any planning horizon measured in tens or hundreds of millions of years. They matter not at all for the ultimate conclusion. Earth will die. The sun will die. Everything on this planet that cannot leave will die with it. The physics governing this transformation operates at the scale of individual atomic nuclei, yet determines the fate of entire worlds. At the core of the Sun, 15 million kilometers below the visible surface we see from Earth, the temperature reaches 15 million degrees Celsius. The pressure is 250 billion times Earth's atmospheric pressure at sea level. Under these conditions, hydrogen nuclei, which are simply protons, move fast enough and collide with sufficient force to overcome the electromagnetic repulsion that normally keeps positively charged particles apart. When 4 protons eventually fuse through a series of intermediate steps into a single helium nucleus, the mass of the result is slightly less than the mass of the ingredients. That missing mass, about 0.7% of the original, converts directly into energy according to Einstein's equation. This is where sunlight comes from. This is where all the warmth that makes Earth habitable originates. 4 million tons of matter becoming energy every second. But here is the problem that leads to the sun's slow brightening. Helium nuclei are heavier than hydrogen nuclei. As fusion proceeds, helium accumulates in the core. It just sits there because the temperature is not yet high enough to fuse helium into heavier elements. That requires about 100 million degrees Celsius, 10 times hotter than the sun's current core. So the helium builds up, making the core denser and more compact. This creates a feedback effect. The denser core has stronger gravity, which pulls the surrounding hydrogen layer inward more forcefully. This compression heats the hydrogen and increases the rate of fusion in a shell around the helium core. More fusion means more energy output. More energy output means the sun slowly grows brighter. The process is gradual and stable, kept in check by the star's structure, but it is also inexorable. Every second that passes, every 4 million tons of hydrogen that fuses into helium, the core becomes fractionally denser, and the fusion rate creeps fractionally higher. Think of it like this. Imagine a fire burning in a fireplace. If you compress the wood and coals down into a tighter space, the fire burns hotter because the fuel is packed more densely. But if you compress it too much, you might smother it. A star does not have this problem because it has no external walls, no container. Gravity provides the compression, and gravity is always pulling inward. The star can keep compressing its core and burning hotter until it runs out of fuel, or until the core becomes dense enough to generate degeneracy pressure, which is a quantum mechanical effect that eventually halts the collapse. For the sun, still in the middle of its main sequence lifetime, this gradual core compression and brightening will continue for another 5 billion years. The rate of increase is approximately 1% additional brightness every 100 million years. This sounds negligible until you multiply it across hundreds of millions of years and consider the delicate balance of Earth's climate system. The mechanism that ends complex life on Earth billions of years before the sun's red giant phase involves the interaction between stellar radiation, planetary atmospheres, and water. Water is peculiar among common molecules. It exists as solid, liquid, and gas within a relatively narrow temperature range, and that range happens to overlap with the temperatures found on Earth's surface. This is not a coincidence. Earth's distance from the sun, combined with the greenhouse effect of its atmosphere, places surface temperatures in the sweet spot where water can exist in all 3 phases. Liquid water is essential for all known forms of life. It is the solvent in which biochemistry happens. When planetary scientists define the habitable zone around a star, they are really defining the range of orbital distances where liquid water can exist on a planetary surface. Earth sits comfortably in the middle of the Sun's habitable zone right now. But as the Sun brightens, the habitable zone moves outward. In roughly 1 billion years, the inner edge of the habitable zone will move beyond Earth's orbit. At that point, the planet transitions from habitable to uninhabitable, not because something catastrophic happens suddenly, but because the equilibrium conditions no longer permit liquid water. The transition begins with increased evaporation. As solar radiation increases, more water evaporates from the oceans and enters the atmosphere as vapor. Water vapor is transparent to visible light, but absorbs infrared radiation, the heat that Earth radiates back towards space. This means more water vapor in the atmosphere traps more heat, which warms the planet, which causes more evaporation. Under current conditions, this feedback is limited by other atmospheric processes. Clouds form and reflect sunlight. Precipitation returns water to the surface. The system maintains a rough balance. But as solar radiation increases beyond a certain threshold, the balance breaks. The atmosphere can hold more water vapor at higher temperatures. If enough water vapor accumulates, the atmospheric temperature profile changes in a way that prevents clouds from forming as efficiently. More sunlight reaches the surface. More water evaporates. The feedback accelerates. Eventually, the surface temperature exceeds the boiling point of water. The oceans literally boil. What happens next is perhaps even more devastating in the long term. When water vapor reaches the stratosphere, the upper layer of the atmosphere where ozone exists, ultraviolet radiation from the sun breaks the water molecules apart. This is called photodissociation. A water molecule consists of 2 hydrogen atoms bonded to 1 oxygen atom. Ultraviolet photons carry enough energy to sever these bonds. The result is free hydrogen and free oxygen in the upper atmosphere. Hydrogen is the lightest element. At the temperatures found in the stratosphere, especially in a warming world, hydrogen atoms move fast enough to escape Earth's gravity entirely. They simply leave, drifting up through the exosphere and into interplanetary space. This process is called atmospheric escape, and it is irreversible. Once hydrogen atoms leave Earth's gravity well, they are gone. Over millions of years, an entire ocean's worth of hydrogen can be lost this way. The oxygen left behind reacts with surface rocks, forming oxides. The planet loses its water permanently. This is not speculation about what might happen under extreme conditions. We have an example of this process in our own solar system. Venus is nearly identical to Earth in size and mass, and it formed at roughly the same time from the same material. Venus orbits the Sun at a distance of 108 million kilometers, compared to Earth's 150 million kilometers. This places Venus closer to the inner edge of the habitable zone, receiving about twice as much solar radiation as Earth. At some point in Venus's history, likely billions of years ago, it experienced a runaway greenhouse effect. The evidence is visible today. Venus's atmosphere is 96% carbon dioxide, with a surface pressure 90 times greater than Earth's. The surface temperature averages 467 degrees Celsius, hot enough to melt lead. Measurements from various Venus missions, including the Soviet Venera landers in the 1970s and 1980s and NASA's Magellan orbiter in the 1990s, show that Venus has almost no water. The ratio of deuterium, which is heavy hydrogen, to normal hydrogen in Venus's tiny remaining water content is about 150 times higher than on Earth. This is exactly what you would expect if Venus lost most of its hydrogen to space, while the heavier deuterium stayed behind. Venus is Earth's future, just moved forward in time by the planet's closer proximity to the Sun. The calculations showing when Earth experiences its own runaway greenhouse depend on several factors that are not perfectly known. The exact brightness at which the feedback becomes self-sustaining depends on cloud behavior, which is one of the largest uncertainties in climate modeling even for current conditions. It depends on atmospheric composition, particularly the amount of carbon dioxide, which varies naturally over geological timescales due to volcanic activity and silicate weathering. It depends on Earth's reflectivity, called albedo, which changes with ice cover, vegetation, and atmospheric aerosols. Different models incorporating different assumptions about these factors give estimates ranging from as soon as 500 million years to as late as 1.5 billion years for when the runaway greenhouse begins. But all models agree that it happens well before the Sun becomes a red giant. The window for complex life on Earth is measured in hundreds of millions of years, not billions. There is a counterintuitive aspect to this timeline that makes it even more unsettling. Carbon dioxide levels in Earth's atmosphere have been declining over geological time. This happens because of the carbonate-silicate cycle. Rain combines with carbon dioxide to form carbonic acid, which is a weak acid. This acid weathers silicate rocks, releasing calcium and other ions. These ions wash into the ocean, where marine organisms use them to build shells and skeletons made of calcium carbonate. When these organisms die, their shells sink and eventually form sedimentary rock like limestone. This removes carbon dioxide from the atmosphere and locks it in rock. Volcanic activity releases some of this carbon dioxide back into the atmosphere, but the balance over hundreds of millions of years favors sequestration. The geological record shows that carbon dioxide levels were much higher in the deep past. Early Earth had an atmosphere with perhaps 10% or more carbon dioxide, compared to about 0.04% today, before human industrial emissions. This decline in carbon dioxide is paradoxical because carbon dioxide is a greenhouse gas. Less carbon dioxide should mean a cooler planet. But the Sun has been brightening and the two effects roughly balance. Earth's climate has remained within habitable bounds for billions of years because declining carbon dioxide compensated for increasing solar radiation. Here is where it gets uncomfortable. As the Sun continues to brighten, Earth will need even less carbon dioxide to maintain current temperatures. But there is a lower limit to how much carbon dioxide can exist in the atmosphere while still supporting the plants that form the base of the food chain. Most plants use a photosynthetic pathway called C3 that requires carbon dioxide concentrations above about 150 parts per million to function efficiently. Below that threshold, C3 photosynthesis becomes difficult. Many plants would die. Some researchers estimate that carbon dioxide levels could fall below this threshold in as little as 500 million to 800 million years, possibly sooner. At that point, most terrestrial plant life collapses. Without plants producing oxygen and serving as the foundation of ecosystems, complex animal life becomes impossible. The planet might still be technically habitable in the sense that the oceans have not boiled, but the biosphere as we know it ceases to exist. Then, as the Sun continues brightening and carbon dioxide levels cannot fall any further, the temperature begins to rise unchecked. The runaway greenhouse becomes inevitable. The timeline is uncertain in its specifics, but certain in its outcome. Earth's habitability is finite. The mechanisms are understood. The physics is straightforward. What remains unclear is exactly when the various tipping points arrive and in what order. Does the carbon dioxide crisis hit first, causing a biosphere collapse before the runaway greenhouse? Or does warming accelerate ecosystem decline, which reduces carbon dioxide absorption by dying plants, which accelerates warming? The feedback loops intertwine in complex ways, but the end result is the same. Within 1 billion years at most, likely much sooner, Earth transitions from a living world to a dead one. The transition might take tens of millions of years as conditions gradually worsen, or it might happen relatively quickly in geological terms, just a few million years, once certain thresholds are crossed. Either way, any form of life that cannot adapt to these changing conditions or leave the planet entirely faces extinction. This understanding emerged slowly from multiple lines of research over the past several decades, building on earlier work about stellar evolution and planetary atmospheres going back to the mid-20th century. The pieces came together as scientists studied Venus more closely, as climate models became sophisticated enough to simulate extreme scenarios, and as the search for exoplanets forced researchers to think carefully about what makes a planet habitable. The realization that Earth's habitability has an expiration date is relatively recent in scientific terms, emerging clearly only in the past 30 to 40 years. Before that, the focus was on the Sun's eventual red giant phase, 5 billion years away, which seemed too distant to contemplate seriously. The recognition that Earth becomes uninhabitable long before the Sun dies is a product of late 20th and early 21st century planetary science. It is. This understanding sits on a foundation of stellar physics that took most of the 20th century to construct, in Nenukt. In 1920, Arthur Eddington, working at Cambridge University, proposed that stars derive their energy from the fusion of hydrogen into helium. This was a radical idea at the time. The existence of atomic nuclei had been confirmed only 9 years earlier by Ernest Rutherford. The concept that nuclei could fuse together under extreme conditions, releasing enormous amounts of energy in the process, represented a fundamental breakthrough in understanding how the sun could shine for billions of years without exhausting its fuel. Eddington's proposal was initially controversial. Many physicists doubted that stellar interiors could reach temperatures high enough for fusion to occur. But Eddington was correct, though the detailed mechanisms would not be worked out for another 2 decades. In 1938, Hans Bethe, a German-American physicist who would later win the Nobel Prize, published the first complete description of the nuclear reactions that power stars like the Sun. Bethe identified what is now called the proton-proton chain, the sequence of fusion reactions that converts hydrogen into helium in stars, with masses similar to or less than the Sun's mass. The proton-proton chain proceeds through several steps. First, 2 protons fuse to form deuterium, releasing a positron and a neutrino. The deuterium then fuses with another proton to form helium-3, releasing a gamma ray. Finally, 2 helium-3 nuclei fuse to form helium-4, releasing 2 protons that can re-enter the cycle. Bethe calculated the energy released by these reactions and showed that they could account for the Sun's observed luminosity. This work laid the foundation for all subsequent research on stellar evolution. It explained not just how the Sun shines now, but how it must change over time as hydrogen converts to helium and the core composition shifts. The first detailed models of stellar evolution emerged in the 1950s and 1960s as electronic computers became available for scientific research. In 1952, Martin Schwarzschild at Princeton University published calculations showing how stars evolve off the main sequence after exhausting hydrogen in their cores. His work demonstrated that stars like the Sun eventually expand into red giants, though the timescales involved were still uncertain. Throughout the 1960s, teams of astrophysicists, including Iko Iben at MIT and Fred Hoyle and his collaborators in Britain, developed increasingly sophisticated stellar evolution codes. These programs could track the changes in a star's structure and composition over billions of years, calculating temperature, pressure, and density at thousands of points from the core to the surface. The models showed clearly that main sequence stars brighten gradually as helium accumulates in their cores, exactly as Beth's fusion calculations predicted. By the 1970s, stellar evolution models had become accurate enough to make detailed predictions about the Sun's past and future. In 1972, Iko Eben published a comprehensive study of the Sun's evolution that remains foundational. Eben's models showed that the Sun was approximately 30% dimmer when it first began fusing hydrogen 4.6 billion years ago. This created what became known as the faint young sun paradox. Geological evidence clearly showed that Earth had liquid water and possibly life as early as 3.8 billion years ago. Yet a sun 30% dimmer should have meant a frozen Earth with average temperatures well below 0 Celsius. The resolution of this paradox involved recognizing that Earth's atmosphere was very different in the past, with much higher concentrations of greenhouse gases like carbon dioxide and methane that kept the planet warm despite reduced solar radiation. This realization connected stellar evolution directly to planetary climate and habitability. The understanding of how stars end their lives advanced significantly with observations in the 1980s and 1990s. The Hubble Space Telescope, launched in 1990, provided unprecedented images of planetary nebulae, the glowing shells of gas ejected by dying stars. These observations confirmed that Sun-like stars lose their outer layers near the end of their lives, leaving behind white dwarf cores. The physics of this mass loss became clearer. As a star evolves into a red giant, its outer layers become loosely bound because the star's radius increases dramatically, while its total mass remains nearly constant. Stellar winds driven by radiation pressure and pulsations gradually blow away the outer envelope. For a star like the Sun, models suggested that about 40 to 50% of its mass would be lost during the red giant and subsequent asymptotic giant branch phases. This mass loss is crucial for understanding what happens to the planets. The question of Earth's ultimate fate during the Sun's red giant phase remained uncertain through the 1990s and early 2000s. The uncertainty arose from two competing effects. As the Sun loses mass, its gravitational pull on the planets weakens. This causes planetary orbits to spiral outward, moving Earth farther from the Sun. At the same time, the Sun expands dramatically. Which effect wins determines whether Earth gets swallowed or survives as a scorched remnant. In 2001, Klaus-Peter Schroeder of the University of Guanajuato in Mexico and Robert Conan Smith of the University of Sussex published detailed calculations addressing this question. They incorporated the effects of tidal forces between the red giant Sun and the planets, which had been neglected in earlier studies. Tidal interactions transfer angular momentum from the Sun's rotation to the planetary orbits, but they also cause orbital decay through friction. Schroeder and Smith's models suggested that Earth would likely be engulfed during the red giant phase, though the uncertainties were large enough that survival as a barren rock remained possible. More recent simulations using increasingly powerful computers have refined these estimates without eliminating the uncertainty. In 2008, a team led by Laughlin at the University of California, Santa Cruz published models showing that Earth's fate depends sensitively on the exact rate of solar mass loss, which remains difficult to predict precisely. If the Sun loses mass faster during its red giant phase, Earth's orbit expands more and survival becomes more likely. If mass loss proceeds more slowly, Earth gets engulfed, The difference between these scenarios amounts to variations of just a few percent in the mass loss rate, which is within the uncertainty of current models. Observations of other stars in their red giant phases provide some constraints, but every star is slightly different. The best current estimate is that Earth has perhaps a 50% chance of physical survival, but this is meaningless from a habitability perspective, because the planet will have been sterilized billions of years earlier. The recognition that Earth becomes uninhabitable long before the Sun's red giant phase emerged from studies of planetary habitability that accelerated in the 1980s and 1990s. In 1984, Michael Hart, then at the National Center for Atmospheric Research in Colorado, published one of the first systematic studies of the habitable zone around the Sun. Hart's models considered how the habitable zone boundaries change as the Sun brightens over billions of years. He found that Earth sits near the inner edge of the continuously habitable zone, the region where a planet can maintain liquid water throughout the Sun's main sequence lifetime. Hart's work suggested that a planet only 5% closer to the Sun than Earth would have experienced a runaway greenhouse effect early in its history. This highlighted how sensitive planetary habitability is to orbital distance and stellar luminosity. James Casting at Penn State significantly advanced this field in the late 1980s and early 1990s. Casting developed detailed atmospheric models that could simulate the coupled evolution of planetary climates and stellar brightness over billions of years. His 1988 paper in the journal Icarus presented the first rigorous calculations of when Earth would lose its oceans to a runaway greenhouse effect. Casting's models incorporated detailed atmospheric chemistry, cloud feedback effects, and the carbonate-silicate cycle that regulates carbon dioxide levels. The results showed that Earth would transition to a runaway greenhouse state in roughly 1 billion years as the Sun's luminosity increased. This timeline was shorter than many scientists expected. It meant that Earth's habitability was limited not by the Sun's death in 5 billion years, but by atmospheric physics operating on timescales of 1 billion years or less. Subsequent research refined these estimates and identified additional mechanisms that could shorten the habitability window even further. In 1992, James Lovelock and Michael Whitfield published a paper arguing that carbon dioxide decline due to silicate weathering could cause a biosphere collapse within several 100 million years, well before the runaway greenhouse begins. Their models showed that as the Sun brightens, Earth needs progressively less atmospheric carbon dioxide to maintain habitable temperatures. But plants and photosynthetic organisms require minimum carbon dioxide concentrations to function. Once atmospheric carbon dioxide falls below this threshold, plant life collapses, oxygen production ceases, and complex ecosystems disappear. Lovelock and Whitfield estimated this could happen in as little as 500 million to 1 billion years. This research suggested that Earth faces multiple routes to becoming uninhabitable, with different mechanisms operating on similar timescales. The discovery of thousands of exoplanets beginning in the 1990s forced planetary scientists to think more carefully about habitability criteria. The first confirmed exoplanet around a Sun-like star came in 1995 when Michel Mayor and Didier Queloz discovered a giant planet orbiting 51 Pegasi. This discovery opened the floodgates. The Kepler Space Telescope, launched in 2009, discovered thousands more planets by detecting the tiny dips in starlight as planets transit across their host stars. Many of these planets orbit in their stars' habitable zones, raising questions about what factors beyond liquid water determine whether life can emerge and persist. Studies of habitable zones around stars of different masses showed that stellar evolution poses a universal challenge. All stars brighten as they age. All habitable zones migrate outward. Any planet that starts near the inner edge of the habitable zone eventually becomes uninhabitable, often long before the star exhausts its fuel. The characterization of Venus's atmosphere by multiple spacecraft missions provided crucial data for understanding runaway greenhouse effects. NASA's Pioneer Venus mission, which arrived at Venus in 1978, carried instruments that measured the atmosphere's composition, temperature, and pressure profile from orbit and with atmospheric probes. The data confirmed that Venus experienced catastrophic water loss. The Soviet Venera missions, particularly Venera 13 and Venera 14 in 1982, successfully landed on Venus's surface and measured temperatures exceeding 450 degrees Celsius before succumbing to the extreme conditions. The European Space Agency's Venus Express, which orbited Venus from 2006 to 2014, detected the high deuterium to hydrogen ratio that serves as a signature of massive hydrogen escape. These missions painted a picture of a planet that once might have had oceans but lost them to a runaway greenhouse effect, becoming the hellish world we see today. In 2011, Ravi Kopparapu and colleagues published updated habitable zone calculations that incorporated advances in atmospheric modeling and climate science from the intervening decades since Casting's pioneering work. Kopparapu's team used three-dimensional climate models rather than the one-dimensional models available earlier. They found that the inner edge of the habitable zone around the Sun sits at approximately 0.95 astronomical units, where 1 astronomical unit equals Earth's current orbital distance. Earth orbits at 1 astronomical unit. This means Earth is only 5% farther from the Sun than the inner habitable zone boundary. The margin is razor thin. As the Sun brightens, this boundary moves outward. Kopparapu's models suggested Earth crosses into uninhabitable territory within approximately 1 billion years, consistent with Casting's earlier estimates but with greater confidence in the physical mechanisms. The most recent research has focused on identifying potential escape routes or life extension mechanisms for Earth's biosphere. In 2015, a team led by Ramses Ramirez at Cornell University examined whether atmospheric composition changes could extend habitability. They found that if carbon dioxide levels could somehow be maintained at optimal levels, or if other greenhouse gases were introduced, Earth might remain habitable for an additional few hundred million years beyond the standard estimates. However, these scenarios require active intervention or highly specific natural processes. Without such measures, the standard timeline holds. More provocatively, some researchers have explored whether advanced civilizations could engage in planetary engineering to extend habitability, perhaps by using giant reflectors to reduce solar radiation, or by gradually moving Earth's orbit outward as the Sun brightens. These ideas remain speculative but highlight that the timeline for Earth's habitability, while determined by physics, might not be absolutely fixed if technological capability advances sufficiently. What emerges from this century of research is a picture of Earth's future that is detailed, quantitative, and sobering. The Sun will continue brightening at a rate of approximately 1% per 100 million years. In 500 million to 1 billion years, atmospheric carbon dioxide will fall below levels needed to sustain most plant life. Within 1 billion to 1.5 billion years, Earth will experience a runaway greenhouse effect, losing its oceans to space. In 5 to 6 billion years, the Sun will expand into a red giant, possibly engulfing Earth entirely or leaving it as a dead cinder. Each of these stages is supported by extensive modeling, observations of other stars and planets, and laboratory measurements of the relevant physics and chemistry. The uncertainty lies in the exact timing and the relative importance of different mechanisms, not in whether these events will occur. This research emerged from converging lines of investigation spanning astrophysics, planetary science, atmospheric chemistry, and climate modeling. It represents one of the most complete predictions science has ever made about the distant future. We know what will happen to the Sun, to Earth, and to any life that remains on this planet if conditions do not change dramatically. The knowledge is both remarkable and melancholic. Remarkable because it demonstrates the power of scientific reasoning to peer billions of years into the future using only present observations and physical laws. Melancholic because it reveals the impermanence of everything we know, everything we are, everything we might build or discover or create on this world. The timeline gives us perspective. It shows us that Earth is not eternal, that the conditions permitting complex life are temporary, that the window of opportunity is finite, and this perspective forces us to confront Earth's position, not just in space, but in time. When we think about our place in the universe, we typically focus on spatial location. Earth orbits the Sun, which sits in the Orion arm of the Milky Way galaxy, roughly 26,000 light-years from the galactic center. We are not at the center, not at the edge, not anywhere particularly special in terms of location. This ordinariness has been a recurring theme in cosmology since Copernicus removed Earth from the center of the solar system nearly 500 years ago. But the temporal position is equally important and considerably stranger. We exist at a very specific moment in cosmic history, and that moment happens to coincide with a narrow window of habitability on our planet. The universe is approximately 13.8 billion years old, determined by measurements of the cosmic microwave background, by the Planck satellite and other observations. The Sun and Earth formed 4.6 billion years ago, roughly 1/3 of the way through the universe's current age. Complex life on Earth emerged much more recently. The first multicellular organisms appeared around 600 million years ago during the Ediacaran period. Animals with hard body parts and complex ecologies emerged in the Cambrian explosion roughly 540 million years ago. Land plants appeared around 470 million years ago. The entire history of complex visible life on Earth spans only about 12% of Earth's existence and only 4% of the universe's age. We are latecomers on a young planet orbiting a middle-aged star in a universe that still has trillions of years of existence ahead of it. But here is the paradox. Earth's window for complex life is closing. Within the next 1 billion years, likely sooner, conditions become impossible for anything resembling current biology. This means that the total span of complex life on Earth, from the Cambrian explosion to the final extinction, will be roughly 1.1 to 1.5 billion years. Compare this to the age of the universe. Complex life on Earth will have existed for only about 8 to 11% of cosmic time from the Big Bang to the end of Earth's habitability. That is a remarkably narrow window. If you compress the universe's history into a single year, complex life on Earth would exist for about 1 month, appearing in early December and going extinct before the new year. And if you consider the universe's future, which could extend for trillions of years or more as stars continue to form and burn out slowly, Earth's era of complex life becomes an almost infinitesimal blip. This raises an uncomfortable question that planetary scientists and astrobiologists have begun to examine more carefully in recent years. Are we typical or special? Is Earth's approximately 1 billion year window for complex life normal for habitable planets? Or is it unusually short, or perhaps unusually long? The answer depends on factors we are only beginning to understand. Stellar lifetime is one constraint. Stars more massive than the Sun burn hotter and brighter but exhaust their fuel much faster. A star twice the Sun's mass might last only 2 billion years on the main sequence, giving its planets less time to develop life. A star half the Sun's mass could last 20 billion years or more, potentially allowing much longer windows for habitability. But smaller stars have their own problems. They tend to be more active when young, producing powerful flares that could strip away planetary atmospheres. The habitable zone around a small star is much closer to the star, which means tidal forces might lock planets into synchronous rotation with one side always facing the star. This could create extreme temperature differences that make habitability difficult. The geological activity of a planet also matters profoundly. Earth has plate tectonics, the slow movement of crustal plates driven by heat from the planet's interior. Plate tectonics recycles carbon dioxide through the carbonate-silicate cycle, regulating atmospheric composition over geological time. Plate tectonics also generates a magnetic field through the motion of molten iron in Earth's outer core. This magnetic field shields the atmosphere from the solar wind, preventing atmospheric erosion. Not all planets have plate tectonics. Venus does not, which may have contributed to its runaway greenhouse by allowing carbon dioxide to accumulate without geological recycling. Mars lost its magnetic field early in its history, which allowed the solar wind to strip away much of its atmosphere, transforming it from a potentially habitable world to the cold, dry desert we see today. The factors that determine whether a planet maintains geological activity over billions of years are complex and depend on planetary size, composition, and thermal history. Earth may be fortunate in this regard, or it may be typical. We do not yet know. The timing of life's emergence on Earth provides another piece of the puzzle. The oldest evidence for life on Earth comes from rocks approximately 3.8 billion years old, though the evidence at this age is somewhat controversial. By 3.5 billion years ago, life definitely existed in the form of simple bacterial cells. This means life emerged relatively quickly after Earth cooled enough to have liquid water. The planet formed 4.6 billion years ago. The first billion years were chaotic, with frequent asteroid and comet impacts, including the collision that formed the Moon roughly 4.5 billion years ago. Once conditions stabilized, life appeared within a few 100 million years. This rapid emergence suggests that the transition from chemistry to biology might not be particularly difficult, given the right conditions. If true, this would imply that habitable planets commonly develop life early in their histories. But the transition from simple, single-celled life to complex, multicellular life took much longer. For roughly 3 billion years, life on Earth consisted entirely of bacteria and archaea, single-celled organisms without nuclei. Complex cells with nuclei, called eukaryotes, appeared around 2 billion years ago. Multicellular organisms built from many eukaryotic cells working together did not emerge until around 600 million years ago. The reasons for this enormous delay remain unclear. Some researchers argue that the evolution of complex life requires specific environmental conditions, such as sufficient atmospheric oxygen, which only accumulated slowly as photosynthetic bacteria gradually transformed the atmosphere. Others suggest that certain evolutionary innovations, like the origin of the eukaryotic cell itself, are extremely rare chance events. If complex life requires multiple unlikely steps, then most habitable planets might remain stuck in a bacterial phase throughout their entire habitable windows. Earth's relatively rapid progression to complex life could be unusual. This connects to a broader question in astrobiology called the Great Filter. The Fermi paradox, named after physicist Enrico Fermi, asks why we see no evidence of intelligent extraterrestrial civilizations despite the enormous number of stars and planets in the galaxy. If life and intelligence are common, the galaxy should be filled with civilizations, some of them much older and more advanced than us. Where are they? One possible answer is the Great Filter hypothesis, which suggests that there is at least one extremely difficult step in the evolution of life that acts as a filter, allowing very few planets to reach advanced civilizations. The question is where this filter sits. Is it behind us, in the origin of life, or the evolution of complex cells? Or is it ahead of us in the development of intelligence, the creation of technological civilizations, or the survival of such civilizations over long timescales? The finite habitability window adds another layer to this question. Even if life commonly emerges on habitable planets, and even if complex life commonly evolves, the window for developing intelligence and technology might be narrower than we think. On Earth, intelligence capable of creating technology emerged only in the last few 100,000 years, right at the end of the habitable window. We appeared roughly 4 billion years into Earth's 4.5 billion year habitability period. We are using up most of the available time. If intelligence typically requires billions of years to evolve, then many planets might run out of time before reaching this stage. The sun's brightening imposes a deadline. Biology must either develop spacefaring capability before the planet becomes uninhabitable, or it goes extinct. There is no third option. The window is closing, and for most of that window, life on Earth was microbial, incapable of responding to the crisis. Our position in time also affects what we can observe about the universe. We exist during an era when the cosmic microwave background is still visible, when distant galaxies are still observable, when the expansion history of the universe can be studied through supernova observations and other techniques. In the far future, trillions of years from now, the expansion of the universe will have carried most galaxies beyond the observable horizon. The cosmic microwave background will have redshifted into undetectability. Future civilizations arising in that era would have no evidence of the Big Bang, no way to study the early universe, no ability to measure cosmic expansion. They would inhabit isolated galaxy clusters surrounded by darkness, with no way to deduce the cosmic context they exist within. We are privileged to live in an era when the universe reveals its history. This privilege is temporary. The measurement of Earth's future habitability depends on multiple interconnected systems, each with its own uncertainties. Climate models must simulate atmospheric composition, cloud formation, ocean circulation, and ice sheet dynamics over millions of years. These models are tested against Earth's past climate using geological proxies like ice cores, ocean sediment cores, and ancient rock formations that preserve information about past temperatures and atmospheric conditions. But extrapolating millions of years into the future introduces uncertainties that compound. Small changes in assumptions about cloud feedback or carbon cycle dynamics can shift the habitability deadline by hundreds of millions of years. This is not a failure of science, but a consequence of the complexity of the system being modeled. Stellar evolution models face fewer uncertainties because they depend primarily on well-understood nuclear physics rather than complex fluid dynamics and chemistry. The rate at which the sun brightens is predictable within a few percent. The core temperature and pressure evolution follow from fundamental equations of stellar structure. The main uncertainty in stellar models concerns mass loss during later evolutionary phases, but that affects the red giant stage billions of years in the future, not the gradual brightening over the next billion years. For near-term predictions on 100 million to billion-year timescales, stellar evolution is the more certain component of the system. The interaction between stellar evolution and planetary climate creates feedback effects that complicate predictions. As the sun brightens, Earth must shed more heat to maintain energy balance. This requires either reducing greenhouse gas concentrations or increasing the planet's reflectivity. The carbonate-silicate cycle provides a natural feedback that reduces carbon dioxide as temperature rises, because warmer temperatures accelerate chemical weathering of rocks, which removes carbon dioxide from the atmosphere. This negative feedback has stabilized Earth's climate for billions of years, despite the sun's increasing luminosity. But the feedback has limits. Carbon dioxide concentration cannot fall below the level needed for photosynthesis without collapsing the biosphere. Once this lower limit is reached, the feedback breaks and temperature control is lost. Calculating when this happens requires understanding geological processes, biological evolution, and atmospheric chemistry simultaneously. Secondary effects add further complexity. The biosphere itself influences climate through multiple pathways. Plants affect surface reflectivity, with forests absorbing more sunlight than grasslands or deserts. Plankton in the ocean produce dimethyl sulfide, which seeds cloud formation, increasing reflectivity. Bacteria in soil affect methane and nitrous oxide emissions, both of which are greenhouse gases. As climate changes, these biological feedbacks also change in ways that are difficult to predict over millions of years. Evolution will reshape the biosphere in response to warming, potentially creating new feedback loops or amplifying existing ones. The biosphere is not a passive victim of climate change, but an active participant in the climate system. The location of Earth within the habitable zone makes these processes particularly sensitive to small changes. A planet orbiting farther from the Sun, say at 1.1 or 1.2 astronomical units, would have more time before crossing into runaway greenhouse territory. A planet closer in at 0.9 astronomical units would have already experienced catastrophic warming. Earth sits right at the edge where the sun's gradual brightening matters decisively. This is partly selection bias. If Earth were outside the habitable zone, we would not be here to contemplate it. But it also means that Earth's future is unusually sensitive to the specific details of climate feedbacks and stellar evolution. Small differences in atmospheric composition or cloud properties could shift the habitability deadline significantly. The broader solar system context also matters for understanding Earth's future. The sun's brightening affects all the planets, not just Earth. Venus experienced its runaway greenhouse long ago, and now serves as a preview of Earth's fate. Mars lost most of its atmosphere early in solar system history, and is currently too cold for liquid water on its surface. But as the sun brightens, Mars could potentially become more hospitable, with temperatures rising enough to melt subsurface ice. Jupiter's moon Europa and Saturn's moon Enceladus have subsurface oceans kept liquid by tidal heating from their host planets. These moons exist far from the sun in regions that are currently frozen, but as the sun brightens and eventually enters its red giant phase, the outer solar system will warm dramatically. Some models suggest that moons like Europa could become habitable in the distant future, perhaps billions of years from now, just as Earth becomes uninhabitable. The habitable zone is not fixed, but migrates outward with stellar evolution, potentially creating habitability in places that are currently frozen, while destroying it in places that are currently temperate. This migration raises profound questions about the long-term distribution of life in planetary systems. If complex life typically takes billions of years to evolve, and if habitable zones migrate outward as stars age, then perhaps life never has enough time to adapt to changing conditions. By the time Mars or Europa become habitable from solar warming, Earth's biosphere will have been extinct for billions of years, and there will be no mechanism to transport life from the inner to the outer solar system. Unless life arises independently multiple times in the same planetary system, which seems unlikely, or unless intelligent life develops technology to deliberately spread to newly habitable worlds, each planet has only one chance. If that chance is missed, or if life goes extinct before conditions change, the opportunity is lost permanently. Our temporal position in Earth's history determines what is possible and what is not. We exist during the narrow window when complex life is viable, when intelligence is possible, when technological civilization can emerge. This window is closing. The physics is inexorable. What we do with this window, whether we use it to spread beyond Earth, or whether we exhaust it remaining on a single world, determines whether anything of our lineage survives the coming environmental catastrophe. Not catastrophe in the human sense of sudden disaster, but catastrophe in the planetary sense of irreversible transformation across hundreds of millions of years. The timeline gives us perspective on our significance and our fragility. We are here now during this brief interval when Earth permits complexity, and that interval is already more than halfway finished. The clock has been ticking since complex life began, and the uncertainty in timing creates a tension at the heart of planetary science. Two groups of researchers using equally sophisticated methods to model Earth's future climate arrive at dramatically different conclusions about when habitability ends. The disagreement is not minor. It spans a factor of 2 or more in the timeline. Some models suggest Earth remains habitable for complex life for another 1.3 to 1.5 billion years. Others suggest the window closes in 500 to 800 million years. Both groups have access to the same observational data, the same fundamental physics, the same computational tools. Both have tested their models against Earth's past climate and found reasonable agreement. Yet they reach conclusions that differ by hundreds of millions of years. This is not a small error margin. It represents fundamental uncertainty about processes that will determine the fate of all life on this planet. The first approach uses what are called one-dimensional radiative convective climate models. These models, pioneered by James Casting and others in the late 1980s, treat the atmosphere as a vertical column. They calculate how energy from the sun moves through atmospheric layers, how greenhouse gases absorb and re-emit infrared radiation, how temperature changes with altitude. The models are sophisticated in their treatment of radiative transfer and atmospheric chemistry, tracking dozens of chemical species and hundreds of chemical reactions. They incorporate the carbonate-silicate cycle, the biological carbon cycle, the hydrological cycle. They solve the fundamental equations of energy balance to determine what happens when solar radiation increases over time. Casting's 1988 model, which has been refined continuously over the past 3 decades, suggests that Earth enters a runaway greenhouse state when the sun's luminosity reaches approximately 1.1 times its current value. Given that solar luminosity increases by roughly 1% every 100 million years, this threshold is crossed in approximately 1 billion years. The runaway greenhouse threshold in these models is determined by atmospheric water vapor. As the planet warms, more water evaporates from the oceans. Water vapor is a powerful greenhouse gas. More water vapor means more absorbed infrared radiation, which means higher temperatures, which means more evaporation. The feedback is self-reinforcing. But Earth's atmosphere currently maintains a stable balance because the upper atmosphere is cold enough that water vapor condenses and falls back as precipitation before reaching the stratosphere. This cold trap limits how much water vapor can accumulate aloft. The runaway greenhouse begins when surface temperatures rise enough that the atmospheric temperature profile changes. Instead of getting colder with altitude throughout the troposphere, the temperature remains high enough at all altitudes that water vapor does not condense. At this point, water floods into the stratosphere where ultraviolet radiation breaks it apart. Hydrogen escapes to space. The ocean boils away over geological time. Castings models calculate this threshold occurs when incoming solar radiation reaches about 330 to 340 watts per square meter, compared to about 240 watts per square meter today. The second approach uses three-dimensional general circulation models, the same class of models used to study Earth's current climate and predict future warming from human carbon dioxide emissions. These models divide the atmosphere into a three-dimensional grid, solving equations for fluid motion, heat transfer, and chemical processes at each grid point. They simulate winds, ocean currents, cloud formation, precipitation patterns, ice sheet dynamics. The advantage of three-dimensional models is that they capture spatial variations and feedback processes that one-dimensional models miss. Different regions of Earth respond differently to warming. The tropics might enter a runaway greenhouse state while the poles remain habitable. Ocean circulation patterns shift, affecting heat distribution. Most importantly, three-dimensional models attempt to simulate clouds realistically, and clouds are the largest source of uncertainty in climate prediction. Clouds have a dual effect on climate. They reflect sunlight back to space, which cools the planet. They also trap infrared radiation, which warms the planet. Whether clouds cause net warming or net cooling depends on their altitude, thickness, droplet size, and coverage. Low clouds tend to cool because they are bright and reflect sunlight without being warm enough to emit much infrared radiation. High clouds tend to warm because they are thin enough to let sunlight through but cold enough that they do not radiate much energy to space, acting as an effective blanket. As Earth's climate changes, cloud properties change in complex ways. The altitude distribution shifts, coverage increases in some regions and decreases in others. These changes feed back on temperature, creating effects that are difficult to predict. In 2013, a team led by Jeremy Leconte at the Laboratoire de Météorologie Dynamique in Paris published results from three-dimensional climate simulations of Earth's future. Their models incorporated detailed cloud physics and found something unexpected. The runaway greenhouse threshold might occur at lower solar luminosity than one-dimensional models predict, potentially as low as 1.03 to 1.05 times current solar brightness. This would mean Earth has only 300 to 500 million years of habitability remaining, not 1 billion years. The difference arises primarily from how the models treat clouds. Leconte's three-dimensional simulations showed that as Earth warms, subtropical cloud coverage decreases significantly. Less cloud coverage means less sunlight reflected back to space, which means the planet absorbs more solar energy than one-dimensional models account for. This positive feedback accelerates warming and brings the runaway greenhouse threshold closer. Other three-dimensional modeling efforts have reached different conclusions. In 2016, researchers at the University of Chicago published simulations suggesting that increasing cloud coverage at high latitudes could actually delay the runaway greenhouse by reflecting more sunlight, potentially extending habitability by a few 100 million years beyond Castings' estimates. Their models showed that as polar regions warm, more water evaporates there, leading to increased cloud formation at high latitudes where clouds have a strong cooling effect. This negative feedback partially compensates for the positive feedbacks from water vapor and decreased subtropical clouds. The disagreement between these studies, both using sophisticated three-dimensional models, illustrates the profound uncertainty surrounding cloud behavior in extreme climate states. The magnitude of this disagreement matters enormously. A factor of 2 difference in habitability timeline from 500 million to 1 billion years represents 500 million years of potential biological evolution, ecosystem development, and opportunity for intelligence to emerge and respond to the crisis. To put this in perspective, 500 million years ago, Earth was in the Cambrian period. There were no land plants, no land animals, no insects, no fish, no trees, nothing with a backbone. In the 500 million years since then, life conquered land, evolved complex nervous systems, developed flight, created social structures, and eventually produced technological civilization. If the pessimistic timeline is correct and Earth has only 500 million years remaining, the window for action is much narrower than if the optimistic timeline of 1.5 billion years is correct. The difference is not academic. It affects how we think about humanity's long-term prospects and the urgency of becoming an interplanetary species. The core reason these models disagree is that cloud physics remains poorly understood, even for current climate conditions, let alone for extreme states Earth has never experienced. Clouds form when water vapor condenses onto tiny particles called cloud condensation nuclei. The number, size, and composition of these particles affect how clouds form, how long they persist, and how much sunlight they reflect. On present-day Earth, cloud condensation nuclei come from sea salt, dust, biological particles, and pollutants. In a future hotter Earth, the sources and properties of these particles will change. Will biological activity increase, producing more cloud-forming particles? Or will it decrease as ecosystems collapse, reducing particle sources? The models must make assumptions about these processes, and different assumptions lead to different cloud predictions, which lead to different habitability timelines. The disagreement extends beyond clouds to another critical issue: the minimum carbon dioxide threshold for photosynthesis. Plants remove carbon dioxide from the atmosphere through photosynthesis, but they require minimum concentrations to do so efficiently. Most plants use a photosynthetic pathway called C3 that becomes inefficient when carbon dioxide drops below about 150 parts per million, compared to roughly 280 parts per million in pre-industrial Earth's atmosphere. Some plants use an alternative pathway called C4 that can function at lower carbon dioxide concentrations, down to perhaps 10 parts per million. The question is whether Earth's biosphere can transition from C3-dominated to C4-dominated as carbon dioxide declines, or whether the transition happens too rapidly for evolution to keep pace. If most plant life dies when carbon dioxide falls below 150 parts per million, the biosphere collapses earlier than if C4 plants can take over and persist to lower concentrations. James Casting and collaborators estimated in 1993 that atmospheric carbon dioxide would fall below the C3 photosynthesis threshold in approximately 500 million to 900 million years, as silicate weathering continues to draw down carbon dioxide while the sun brightens. This would cause a mass extinction of C3 plants, which represent about 85% of plant species today. If C4 plants cannot fully replace them, oxygen production drops, animal life declines, and the biosphere enters a degraded state well before the runaway greenhouse. Other researchers argue that C4 plants, which evolved relatively recently in Earth's history, about 30 to 40 million years ago, could expand to dominate the biosphere, allowing photosynthesis to continue to much lower carbon dioxide levels. The outcome depends on poorly understood factors like how quickly plant communities can adapt and whether other limiting factors like heat stress or water availability prevent C4 expansion even if carbon dioxide levels permit it. the implications of this uncertainty extend far beyond Earth. As astronomers discover thousands of exoplanets and attempt to assess their habitability, they rely on models developed for Earth. If we do not understand Earth's habitability limits within a factor of 2, how can we confidently predict whether a planet orbiting another star is habitable? The habitable zone boundaries used to evaluate exoplanets come directly from the same climate models that disagree about Earth's future. This uncertainty propagates into estimates of how many potentially habitable planets exist in the galaxy. If the conservative timeline is correct and Earth-like planets typically remain habitable for 1 to 1.5 billion years after complex life emerges, that represents one set of probabilities for finding life elsewhere. If the pessimistic timeline is correct and habitability ends after just 500 million years, the window is narrower, and life might be correspondingly rarer. The stakes involve our understanding of how common, long-lived biospheres are in the universe. If Earth is typical, and if Earth's habitability window for complex lifespans only about 1 to 1.5 billion years total, from the Cambrian explosion to final extinction, then most Earth-like planets have similarly limited windows. This would suggest that at any given time, only a small fraction of potentially habitable planets actually host complex life. Most would either be in their pre-complex phase, with only microbial life, or post-complex phase, already sterilized. The probability of finding another civilization becomes vanishingly small if civilizations only arise very late in their planet's habitable windows, and those windows are shorter than previously thought. If technological intelligence typically requires billions of years to evolve, similar to Earth, then most habitable planets run out of time before reaching this stage. Conversely, if some planets orbit stars that evolve more slowly than the Sun, or if some planets have geological or atmospheric feedbacks that extend habitability beyond what Earth experiences, then the window could be longer elsewhere. Red dwarf stars, the most common type of star in the galaxy, have lifetimes of tens to hundreds of billions of years. If planets orbiting red dwarfs can remain habitable for similarly extended periods, they might have vastly more time for life to evolve and civilizations to emerge. But red dwarfs present their own challenges, including frequent flares that could strip atmospheres and tidal locking that creates extreme temperature contrasts. Whether they offer longer habitability windows or different obstacles that shorten windows remains debated. The measurement of Earth's future habitability timeline also affects how we think about humanity's responsibility to preserve and propagate life. If Earth has 1.5 billion years remaining, there is less urgency to develop spacefaring capability quickly. Civilizations could potentially survive on Earth for billions of years before facing existential environmental threats, giving enormous time to develop technology, explore the galaxy, and establish off-world populations. If Earth has only 500 million years remaining, the timeline compresses significantly. While 500 million years still seems impossibly long from a human perspective, it represents the same span of time that has elapsed since the Cambrian explosion. Everything we see in the biological world today evolved during that interval. Whether humanity's descendants have 3 times that interval or only 1 times that interval before Earth becomes uninhabitable affects the cosmic context in which we exist. What both approaches agree on is that habitability is finite and that the timeline is measured in hundreds of millions to low billions of years. The disagreement concerns the specific mechanisms and their relative timing. Will carbon dioxide collapse happen first, or will the runaway greenhouse happen first? Will cloud feedbacks accelerate or delay the transition? Will biological evolution keep pace with changing conditions, or will ecosystems collapse faster than adaptation permits? These questions remain open because they require predicting the behavior of complex systems over timescales far beyond human experience or observational data. The Earth system has never been in the state it will occupy as the sun continues to brighten. We have no analogues to study except Venus, which provides only an endpoint, not the transition process. Comparing climate modeling methodologies and timelines, this understanding partially but the counterintuitive nature of what will happen extends beyond extends beyond modeling uncertainties into the fundamental physics itself. When most people imagine the sun destroying Earth, they picture a sudden catastrophe, a massive flare perhaps, or an explosion that incinerates the planet in seconds. The reality is almost the opposite. The process is glacially slow by human standards, yet inevitable by physical law. The sun does not attack Earth. It simply continues being a star, following the same nuclear processes that have sustained life here for billions of years. The mechanism that eventually sterilizes Earth is not violence, but persistence. The sun just keeps shining, keeps fusing hydrogen, keeps getting fractionally brighter each century, until the accumulation of these tiny changes crosses a threshold from which there is no return. This is not dramatic. This is patient. Think about it this way. Imagine you are in a room with a heater that increases its output by 1% every 100 years. For the first several thousand years, you barely notice. The room temperature rises imperceptibly across generations. Your great-great-great-grandchildren adapt to the slightly warmer conditions. They wear different clothes, adjust their behaviors, modify the environment in small ways. The change continues so gradually that each generation experiences essentially stable conditions during their lifetime, but the heater never stops increasing. After 10,000 years, it is 10% hotter. After 100,000 years, it has doubled. After 1 million years, conditions in the room bear no resemblance to the starting point. Everyone who could survive the original temperature is long dead. The species that evolved to handle the middle temperatures have also gone extinct. Only organisms adapted to extreme heat remain, and even they are approaching their limits. The heater continues increasing. Eventually, the room becomes uninhabitable for any biology. The process was never sudden. It was the accumulation of small changes sustained across time spans that defy human intuition. The sun is that heater, and Earth is the room. The increase is not 1% per 100 years, but 1% per 100 million years. Even more gradual, yet the principle is identical. The timescale is longer, but the outcome is the same. What makes this counterintuitive is that the very process that enables life, stellar fusion, is also the process that will destroy life. There is no malfunction, no deviation from normal stellar behavior. A star does exactly what it should do, and the result is the eventual sterilization of its planets. This creates a strange paradox. Life on Earth exists because the sun provides energy through fusion. Life on Earth ends because the sun provides energy through fusion. The mechanism is the same in both cases. Only the timescale and the accumulated effect differ. Observational evidence for the sun's gradual brightening comes from multiple sources, though we obviously cannot watch the sun evolve over millions of years directly. Instead, astronomers observe thousands of other sun-like stars at different stages of evolution. By measuring the luminosity of stars with different ages, we can reconstruct how stars like the sun change over time. The Hyades cluster, located about 150 light-years from Earth, contains hundreds of stars that formed together about 625 million years ago. The Pleiades cluster, about 440 light-years away, formed about 100 million years ago. The sun-like stars in these clusters are measurably different. Pleiades stars rotate faster, have more surface activity, and for those similar to the Sun in mass, are systematically dimmer than their older Hyades counterparts. The difference matches theoretical predictions. Younger Sun-like stars are dimmer. As they age and accumulate helium in their cores, they brighten. The most direct evidence comes from studying the Sun itself, using helioseismology, the science of measuring oscillations in the Sun's surface that reveal its internal structure. Just as seismologists use earthquake waves to probe Earth's interior, helioseismologists use sound waves traveling through the Sun to map temperature, density, and composition from the core to the surface. The Solar and Heliospheric Observatory spacecraft, known as SOHO, launched in 1995, has measured these oscillations with extraordinary precision for more than 25 years. The data confirm that the Sun's core is indeed accumulating helium. The sound wave patterns change slightly over time in ways consistent with ongoing fusion and core evolution. These measurements directly verify that the Sun is following the predicted evolutionary path. The brightening is not theoretical. It is happening now, measurably, though slowly. Computer simulations of the Sun's future evolution have been refined continuously since the 1970s. Modern stellar evolution codes can track thousands of variables simultaneously, solving equations for nuclear reaction rates, energy transport, convection patterns, and radiation transfer at millions of points throughout the star's interior. These simulations reproduce the Sun's current properties, its luminosity, temperature, radius, and composition, with remarkable accuracy when started with appropriate initial conditions 4.6 billion years ago. The same codes run forward into the future show the Sun brightening steadily for another 5 billion years, before exhausting the hydrogen in its core. At that point, the core contracts and heats up, which ignites hydrogen fusion in a shell around the helium core. This shell burning produces even more energy than core burning, causing the Sun's outer layers to expand dramatically. The red giant phase begins. But here is where simulations and reality might diverge in ways that matter for Earth's fate. The simulations agree on the broad outline of solar evolution, but they disagree on specific details like the exact rate of mass loss during the red giant phase. The Sun's outer atmosphere will be loosely bound during red giant expansion. Solar wind, enhanced by pulsations and radiation pressure, will blow away mass at rates much higher than today. Current models predict the Sun will lose about 30 to 40% of its mass during the red giant and subsequent asymptotic giant branch phases. But the exact rate is uncertain because it depends on complex atmospheric dynamics that are difficult to simulate accurately. A faster mass loss rate means Earth's orbit expands more quickly as the Sun's gravitational pull weakens. A slower rate means the orbit expands less. This uncertainty of a few percent in mass loss rate translates into the difference between Earth being engulfed or barely surviving as a scorched rock. The statistical improbability of Earth's position in the habitable zone adds another counterintuitive element. The habitable zone around the Sun currently extends from approximately 0.95 astronomical units to about 1.37 astronomical units. Earth orbits at 1 astronomical unit, which places it just 5% inside the inner boundary. This is an extraordinarily narrow margin. If Earth had formed just 5% closer to the Sun, at 0.95 astronomical units, it would likely have experienced a runaway greenhouse early in its history, becoming a second Venus. If it had formed 10% farther out, at 1.1 astronomical units, it would have 1 to 200 million more years of habitability before the runaway greenhouse begins. The fact that Earth sits so close to the inner edge seems like either remarkable coincidence or an example of selection bias. We exist here because this is where conditions permit complex life, but that does not explain why Earth formed at this particular distance rather than somewhere else in the Sun's protoplanetary disk. Some researchers have proposed that Earth's position is not coincidental, but is actually optimal for the development of complex life. The argument goes like this. Planets need billions of years of stable, habitable conditions for life to evolve from simple bacteria to complex organisms. If a planet forms too close to the inner habitable zone boundary, it runs out of time too quickly as the brightening star pushes the boundary outward. If it forms too far out near the outer habitable zone boundary, the planet might be too cold early in its history when the star is dimmer, delaying or preventing the origin of life. Earth's position near the inner edge means it has been continuously habitable for the maximum possible time, from very early in the solar system's history until relatively late. A planet farther out might only become habitable billions of years after formation, reducing the total window for biological evolution. This idea, sometimes called the habitable zone optimization hypothesis, suggests that planets capable of developing complex life tend to be found near the inner edge of their star's habitable zones, because that is where the cumulative habitability duration is longest. However, this reasoning has problems. Most notably, it does not account for the fact that the majority of Earth's habitable period has been occupied by single-celled organisms. Complex life emerged only in the last 15% of Earth's history. If the goal is to maximize time for complex life specifically, rather than life in general, then Earth's position provides no obvious advantage. A planet farther out would have a shorter total habitable duration, but potentially more of that duration available for complex life if it somehow evolved complex organisms earlier. The optimization hypothesis also struggles to explain why Venus, even closer to the inner edge, failed to maintain habitability. If being near the inner edge is optimal, Venus should have been at least as successful as Earth, yet it clearly was not. Alternative frameworks for understanding Earth's habitability have been proposed that challenge the conventional view. The Gaia hypothesis, introduced by James Lovelock in the 1970s, suggests that life itself actively regulates planetary conditions to maintain habitability. In this view, the biosphere is not merely a passenger responding to changing environmental conditions, but an active participant that modifies the atmosphere, oceans, and even geological processes to keep the planet habitable. The evidence for this includes the carbonate-silicate cycle, which is mediated by biological weathering, and the production of cloud condensation nuclei by marine organisms, which affects Earth's reflectivity. Lovelock argued that these feedbacks have kept Earth habitable despite the sun's brightening, and that they might continue to do so longer than purely physical models predict. The Gaia hypothesis remains controversial because it seems to imply purpose or foresight on the part of the biosphere, which is difficult to reconcile with Darwinian evolution. Natural selection operates on individual organisms and genes, not on planetary systems. How could selection produce biosphere-level regulation when there is no competition between biospheres? Critics argue that what appears to be regulation is actually just the accumulated result of many independent biological processes that happen to have stabilizing effects. The fact that these effects have maintained habitability for billions of years is remarkable, but does not require invoking planetary-scale selection or purpose. Nevertheless, the Gaia hypothesis highlights that biology and geology are deeply intertwined on Earth, and that predicting the planet's future requires understanding these connections, not just physical climate processes. Modified theories of stellar evolution have also been proposed, though none have gained wide acceptance. Some researchers have speculated that magnetic fields or other poorly understood processes might affect how stars age, potentially slowing the brightening or altering the timeline. Others have suggested that interactions with the solar wind or cosmic rays could influence Earth's climate in ways not captured by current models. These ideas remain speculative because they lack strong observational support, and because the standard model of stellar evolution has been so successful at explaining observations. The Sun is one of the best-studied stars in the universe. Any deviation from standard theory would need to explain not just Earth's future, but also the Sun's current properties and the properties of thousands of similar stars, observed at different evolutionary stages. The bar for overturning stellar evolution theory is very high. What emerges from all these considerations is a picture of profound interconnection between stellar physics, planetary science, atmospheric chemistry, and biology. Earth's habitability depends on a delicate balance between the Sun's energy output, the atmosphere's composition, the planet's reflectivity, and biological feedbacks. The balance has held for billions of years, but it is not permanent. The Sun's gradual brightening, an inevitable consequence of stellar structure and nuclear physics, slowly but inexorably shifts the system toward instability. The timeline for this shift involves uncertainties spanning hundreds of millions of years, but the direction is certain. Earth will become uninhabitable. The mechanisms are understood even if their precise timing remains debated. The counterintuitive aspect is that nothing unusual needs to happen. No catastrophe is required. The Sun simply continues being a normal star, and that normality is sufficient to end all life on this planet given enough time. The statistical improbability is not that Earth will become uninhabitable, which is certain for any planet orbiting a main sequence star. The improbability is that we exist during the narrow window when conditions permit not just life, but complex, intelligent life capable of understanding this predicament. The window opened roughly 540 million years ago with the Cambrian explosion. It will close in 500 million to 1.5 billion years, when conditions deteriorate beyond what complex organisms can tolerate. The total duration is 1 to 2 billion years. We appeared in the last fraction of this window. If humanity had emerged even 100 million years earlier, Earth would have correspondingly more time remaining. If we had emerged 100 million years later, we might find the planet already in irreversible decline. The timing feels almost absurdly precise, which raises the question of how we know any of this with confidence. How do scientists measure processes events? How do scientists measure processes occurring over hundreds of millions of years? How do they predict the brightness of the Sun 1 billion years from now? How do they determine when atmospheric carbon dioxide will fall below critical thresholds or when the runaway greenhouse will begin? The answer lies in a remarkable collection of measurement techniques, space missions, and observational instruments that have been developed and refined over the past century. These tools allow us to peer both backward and forward in time, reconstructing Earth's past and projecting its future with quantifiable precision. The foundation of our knowledge about stellar evolution comes from spectroscopy, the analysis of light to determine composition, temperature, and motion. When light from a star passes through a prism or diffraction grating, it splits into a spectrum showing intensity at different wavelengths. Dark lines appear in this spectrum where specific elements in the star's atmosphere absorb particular wavelengths. Each element produces a unique pattern of absorption lines, like a fingerprint. By measuring which lines appear and how dark they are, astronomers can determine what a star is made of, how hot it is, how fast it is rotating, and how fast it is moving toward or away from us. The technique was developed in the mid-19th century and has been continuously refined ever since. Modern spectrographs can measure wavelengths to precisions of a few parts per billion, detecting tiny shifts caused by planets orbiting the star or subtle changes in the star's properties over time. For the Sun specifically, helioseismology provides the most detailed information about internal structure. The Sun's surface oscillates with periods ranging from about 3 minutes to several hours. These oscillations are sound waves generated by turbulent convection in the outer layers of the Sun. The waves travel through the solar interior, bouncing between the surface and deeper layers, creating interference patterns that appear as oscillations we can measure. Different oscillation modes probe different depths. High-frequency modes stay near the surface. Low-frequency modes penetrate to the core. By measuring thousands of oscillation frequencies simultaneously, scientists can map the Sun's internal temperature, density, and composition as a function of depth. This technique is analogous to how doctors use ultrasound to image internal organs, except the Sun generates its own sound waves that we can detect by measuring tiny Doppler shifts in spectral lines. The Global Oscillation Network Group, known as GONG, began operations in 1995 with 6 telescopes distributed around the world to provide continuous monitoring of solar oscillations. GONG measures velocities on the Sun's surface to accuracies of about 1 meter per second, detecting oscillations with amplitudes of just tens of meters in a star with a diameter of 1.4 million kilometers. The data revealed that the Sun's core, where fusion occurs, has a helium abundance of about 64% by mass, compared to about 25% in the outer layers. This confirms that helium has been accumulating in the core for billions of years, as hydrogen fuses into helium. The measurements also showed that the core temperature is approximately 15.7 million degrees Celsius, consistent with theoretical predictions from nuclear physics. NASA's Solar Dynamics Observatory, launched in February 2010, carries the helioseismic and magnetic imager, which measures oscillations with even higher precision. This instrument takes images of the Sun every 45 seconds, tracking how different regions of the surface move up and down as sound waves pass through. The accumulated data over more than a decade has allowed scientists to detect subtle changes in oscillation frequencies that reveal how the Sun's interior evolves over solar cycle timescales of about 11 years. While these changes are tiny compared to the evolutionary changes occurring over millions of years, they validate that our models of solar structure are accurate enough to detect real variations. If we can measure changes occurring over 11 years, we can reasonably extrapolate to changes occurring over millions of years using the same physical framework. The measurement of stellar ages, crucial for understanding how stars brighten over time, relies on several independent techniques. The most direct method involves star clusters, groups of stars that form together from the same molecular cloud and therefore have the same age. The Hyades cluster, one of the nearest and best studied clusters, has an age determined to be 625 million years, plus or minus 50 million years. This age comes from multiple methods. One approach compares the cluster's stars to theoretical evolutionary tracks. Stars of different masses evolve at different rates. Massive stars evolve quickly and leave the main sequence early, while low-mass stars remain on the main sequence for billions of years. By measuring where the transition occurs in a cluster, the point where stars are just beginning to leave the main sequence, astronomers can determine the cluster's age. Another method uses white dwarfs, the remnant cores of dead stars. The coolest white dwarfs in a cluster must have formed early in the cluster's history, and their temperatures indicate how long they have been cooling, which gives the cluster's age. Measurements of the Earth's past climate provide crucial validation for models predicting future conditions. Ice cores drilled from Antarctica and Greenland contain trapped air bubbles that preserve samples of ancient atmosphere. The deepest Antarctic ice cores reach back about 800,000 years, providing direct measurements of past carbon dioxide concentrations, methane levels, temperature, and dust content. These cores show that carbon dioxide has varied between about 180 and 300 parts per million during Ice Age cycles over the past 800,000 years, driven by changes in Earth's orbit that affect solar energy distribution. But these timescales are far too short to test predictions about the next billion years. For longer timescales, scientists use geological proxies. Ocean sediment cores contain microscopic fossils of plankton that lived in surface waters and then sank to the sea floor when they died. The oxygen isotope ratios in these fossils depend on temperature and ice volume when the organisms were alive. By measuring isotopes in fossil shells of different ages, scientists can reconstruct ocean temperatures going back tens of millions of years. The record shows that Earth was warmer 50 to 60 million years ago during the Paleocene-Eocene thermal maximum, with global temperatures perhaps 8 degrees Celsius higher than today. There were no permanent ice caps. Palm trees grew in Alaska. Ocean temperatures at high latitudes reached about 20 degrees Celsius, yet this period was still within the habitable range for complex life. Coral reefs existed. Mammals diversified rapidly. The planet was hot, but not sterilized. Rock formations provide even longer climate records through chemical weathering signatures. When carbon dioxide levels are high, weathering rates increase because rainwater becomes more acidic. This affects the types of minerals that form and the isotopic composition of carbonates deposited in ancient soils. By analyzing these signatures in rocks hundreds of millions of years old, scientists have reconstructed that carbon dioxide levels during the early Paleozoic era, about 500 million years ago, were 10 to 20 times higher than pre-industrial levels. The sun was about 5% dimmer than today, but the high greenhouse gas levels kept Earth warm enough for life to thrive. This provides crucial validation that the relationship between solar luminosity, greenhouse gases, and temperature works as models predict, at least for conditions Earth has actually experienced. The search for exoplanets has driven the development of instruments capable of detecting tiny signals from distant worlds. The Kepler Space Telescope, launched in March 2009, monitored more than 150,000 stars continuously for over 4 years, measuring their brightness to precisions of about 20 parts per million. When a planet passes in front of its star as seen from Earth, it blocks a tiny fraction of the starlight. For an Earth-sized planet transiting a Sun-like star, the dimming is about 84 parts per million, lasting a few hours. Kepler detected thousands of these transits, confirming the existence of planets ranging from smaller than Earth to larger than Jupiter. The mission discovered that rocky planets in the size range of Earth are common, with estimates suggesting that 20 to 50% of Sun-like stars host at least one rocky planet in or near the habitable zone. NASA's Transiting Exoplanets Survey satellite, known as TESS, launched in April 2018, surveys the entire sky looking for planets around the nearest and brightest stars. TESS has discovered thousands of candidate planets, including dozens of Earth-sized worlds. Some of these planets orbit in their stars' habitable zones, making them targets for atmospheric characterization. The James Webb Space Telescope, launched in December 2021, can analyze the atmospheres of some of these planets using transmission spectroscopy. When a planet transits its star, some starlight passes through the planet's atmosphere before reaching us. Molecules in the atmosphere absorb specific wavelengths, creating absorption lines in the spectrum. By comparing the spectrum during transit to the spectrum outside of transit, scientists can identify which molecules are present. Water vapor, carbon dioxide, methane, and oxygen all have distinctive spectral signatures. In 2023, James Webb detected carbon dioxide in the atmosphere of WASP 39b, a hot gas giant planet about 700 light-years from Earth. This was the first definitive detection of carbon dioxide in an exoplanet atmosphere and validated that the telescope's instruments are sensitive enough to measure atmospheric composition. For smaller, rockier planets, the signals are much weaker and require longer observation times. But within the next decade, James Webb and future telescopes like the Nancy Grace Roman Space Telescope and proposed missions like the Habitable Worlds Observatory should be able to characterize the atmospheres of nearby Earth-sized planets. If any of these planets show signs of water vapor, oxygen, and other biosignatures, it would suggest that Earth-like biospheres exist elsewhere. If they show signs of runaway greenhouse effects with thick carbon dioxide atmospheres and no water, it would provide observational evidence of the processes that will eventually affect Earth. The measurement of solar luminosity over human timescales demonstrates the stability and predictability of the sun's energy output. The Solar Radiation and Climate Experiment, known as SOURCE, operated from 2003 to 2020, measuring the total amount of solar energy reaching Earth's orbit. The instrument measured what is called the total solar irradiance to a precision of better than 0.1%. The average value is about 1,361 watts per square meter. This value varies by about 0.1% over the 11-year solar cycle as sunspots and other activity features come and go. But the average remains remarkably constant. Over the 17 years SOURCE operated, scientists detected no long-term trend in solar irradiance above the noise level, confirming that on timescales of decades, the sun is extraordinarily stable. The brightening that will eventually sterilize Earth is real, but occurs at rates far too slow to detect over human lifetimes. Precision measurements of Earth's energy balance show how sensitive climate is to small changes in incoming solar radiation. Satellites measure both the sunlight absorbed by Earth and the infrared radiation emitted back to space. The difference between these two quantities determines whether the planet is gaining or losing energy. Since 2000, Earth has been in a state of energy imbalance, absorbing about 0.5 to 1 watt per square meter more than it radiates. This excess energy goes into warming the oceans, melting ice, and heating the atmosphere. An imbalance of just 1 watt per square meter, less than 0.1% of the incoming solar energy, is sufficient to drive significant climate change over decades. This demonstrates how finely balanced Earth's climate system is, and how small changes in solar output, accumulated over millions of years, can have profound effects. Computer models simulating Earth's future climate have improved dramatically as computing power has increased. The models used in the 1980s could simulate decades or centuries of climate evolution. Modern models run on supercomputers can simulate millions of years, tracking changes in atmospheric composition, ocean circulation, ice sheets, vegetation, and biogeochemical cycles. The Community Earth System model, developed by the National Center for Atmospheric Research, incorporates dozens of interacting components representing the atmosphere, oceans, land surface, sea ice, and carbon cycle. Running this model forward in time with gradually increasing solar luminosity shows how different feedback processes activate at different stages. First, increased evaporation adds water vapor to the atmosphere. Then, ice sheets melt, reducing albedo. Then vegetation patterns shift as temperature and precipitation zones migrate. Then carbon dioxide drawdown accelerates as weathering increases. Eventually, the feedbacks overwhelm the system's capacity to maintain equilibrium. The precision of these models is limited by uncertainties in cloud physics, as discussed earlier, but also by uncertainties in how Earth's interior will evolve. Plate tectonics depends on heat from Earth's interior driving mantle convection. Over billions of years, Earth is cooling as radioactive decay rates decline and primordial heat is lost to space. Some models suggest plate tectonics could shut down in 1 to 2 billion years, as the mantle becomes too cool to drive convection efficiently. If plate tectonics stops, the carbonate-silicate cycle stops, and carbon dioxide regulation fails. This could either accelerate the climate crisis by allowing carbon dioxide to accumulate from volcanic outgassing without weathering to remove it, or it could slow volcanic outgassing itself, depending on the details. The interior evolution of rocky planets over billions of years remains one of the largest uncertainties in long-term habitability predictions. Future observations will refine these estimates. The European Space Agency's Plato mission, planned for launch in 2026, will search for Earth-like planets around Sun-like stars and measure stellar ages with unprecedented precision. This will allow comparison between stars of different ages and better calibration of stellar evolution models. Ground-based extremely large telescopes currently under construction, including the 30-meter telescope and the extremely large telescope with a 39-meter mirror, will have the light-gathering power and spectral resolution to characterize the atmospheres of nearby rocky planets. If these telescopes can observe planets at different stages of evolution around stars of different ages, we might directly observe the processes that will eventually affect Earth, seeing them play out on other worlds. The characteristic timescales involved span an enormous range. Solar oscillations occur on timescales of minutes. The solar cycle operates over 11 years. Human-caused climate change manifests over decades to centuries. Ice age cycles occur over tens of thousands of years, driven by orbital variations. The gradual decline in Earth's carbon dioxide operates over tens to hundreds of millions of years. The Sun's brightening toward red giant status spans billions of years. No single technique can measure across all these scales. Instead, scientists piece together observations at short timescales, paleoclimate reconstructions at medium timescales, and theoretical models at long timescales, checking that they all connect consistently. The fact that they do connect, that measurements of the Sun today match predictions from stellar evolution models calibrated against other stars, that Earth's past climate matches models of how the Sun used to be dimmer, gives confidence that the framework is correct. The measurements are indirect, but converge on the same cataloging case studies and recent discoveries. And case studies and comparative analysis. The measurements are indirect, but converge on the same conclusions, which gains additional weight when we examine other worlds that have already experienced versions of Earth's future. Venus stands as the most obvious case study, a planet nearly identical to Earth in size and mass that underwent catastrophic transformation. Venus has a radius of 6,052 kilometers compared to Earth's 6,371 kilometers. Its mass is 81.5% of Earth's mass. It formed from the same materials at the same time in the same region of the protoplanetary disk. Yet today, Venus is a hellscape with surface temperatures of 467 degrees Celsius and atmospheric pressure 92 times Earth's at sea level. The atmosphere is 96.5% carbon dioxide with clouds of sulfuric acid. No liquid water exists anywhere on the surface or in the atmosphere. The planet rotates once every 243 Earth days, more slowly than it orbits the Sun, and it rotates backward relative to most other planets. Something went catastrophically wrong with Venus, and understanding what happened there illuminates what awaits Earth. The Soviet Venera program provided humanity's first direct measurements of Venus's surface conditions. Venera 7, which landed in December 1970, survived for 23 minutes before succumbing to heat and pressure, long enough to transmit temperature and pressure readings that shocked scientists. Earlier missions had suggested Venus was hot, but the reality exceeded predictions. Venera 9 and Venera 10, landing in October 1975, returned the first images from Venus's surface, showing flat rocks and volcanic terrain under orange-tinted light filtered through the thick atmosphere. Venera 13 and Venera 14, landing in March 1982, survived for over an hour each and returned color images showing more detail. The rocks appeared basaltic, similar to volcanic rocks on Earth, suggesting Venus had active or recently active volcanism. The sky glowed orange from scattered sunlight. The landscape looked alien yet somehow familiar, like Earth after some unimaginable disaster. Pioneer Venus, arriving in December 1978, carried instruments that revolutionized understanding of Venus's atmospheric composition. The orbiter and atmospheric probes measured trace gases and isotope ratios that told a story of water loss. Normal water contains hydrogen with 1 proton. Heavy water contains deuterium, an isotope of hydrogen with 1 proton and 1 neutron. On Earth, the ratio of deuterium to hydrogen in water is about 1 part in 6,400. On Venus, the ratio is 150 times higher, meaning that for every 1 normal hydrogen atom, there are significantly more deuterium atoms relative to Earth. This cannot be explained by Venus forming with different initial composition. The solar system's water all came from the same sources, comets and asteroids with similar isotopic ratios. The only explanation is that Venus lost most of its hydrogen to space through atmospheric escape. Ultraviolet radiation broke water molecules apart. Hydrogen escaped because it is light, and deuterium stayed behind because it is heavier and escapes less readily. The remaining water is enriched in deuterium. This is the signature of a world that once had water and lost it. But here is what makes Venus particularly instructive. The planet sits at 0.723 astronomical units from the Sun, receiving about twice as much solar radiation as Earth. This places Venus near the inner edge of the habitable zone, but not necessarily outside it. Some climate models suggest that Venus could have maintained liquid water on its surface for billions of years if it had the right atmospheric composition and rotation rate. A slowly rotating Venus with thick clouds could have reflected enough sunlight to remain temperate despite high solar flux. Recent modeling work published in 2016 by Michael Way and colleagues at NASA's Goddard Institute for Space Studies suggested that Venus might have been habitable with liquid oceans as recently as 700 million years ago. Their models showed that if Venus had Earth-like topography with shallow oceans and continents, the slow rotation could generate atmospheric circulation patterns that kept clouds on the day side, maintaining habitable temperatures. What triggered Venus's transition from potentially habitable to inferno remains debated. One hypothesis involves volcanic activity. Venus shows extensive evidence of volcanism covering much of its surface. The Magellan spacecraft, which orbited Venus from 1990 to 1994 and used radar to map the surface through the thick clouds, revealed hundreds of thousands of volcanic features. Some researchers propose that a period of intense volcanism around 700 million to 1 billion years ago released enormous amounts of carbon dioxide into the atmosphere. This could have initiated a runaway greenhouse effect. Without plate tectonics to recycle carbon dioxide back into the crust, through subduction, the carbon dioxide accumulated. Water vapor entered the stratosphere, photodissociation destroyed it, hydrogen escaped, and Venus lost its oceans. The volcanic hypothesis remains controversial because the timing and intensity of volcanism are uncertain. The surface appears relatively young, with crater counts suggesting an age of only 500 million to 1 billion years. But whether this represents catastrophic resurfacing or gradual renewal is unclear. An alternative hypothesis suggests that Venus never recovered from a runaway greenhouse that occurred very early in solar system history. When Venus formed, the young sun was dimmer than today, but also more active, with stronger ultraviolet output. The combination of high solar radiation at Venus's orbital distance and intense ultraviolet flux could have triggered atmospheric water loss before oceans ever fully formed. In this scenario, Venus was never habitable for more than perhaps a few 100 million years after formation. The planet might have started with significant water, delivered by comets and asteroids during late accretion, but lost it quickly before life had time to emerge. This early loss hypothesis explains why we see no geological evidence of ancient oceans, no sedimentary rocks, no clear water-carved features, though the surface is so young that ancient features might have been erased by volcanic activity. Mars provides a contrasting case study, a planet that was once habitable but lost its habitability through different mechanisms. Mars is much smaller than Earth, with about 11% of Earth's mass and 53% of Earth's radius. This smaller size meant Mars cooled faster. The planet's interior lost heat more rapidly, shutting down the magnetic field generated by a molten core. Without a magnetic field to deflect the solar wind, Mars's atmosphere was gradually stripped away. Measurements by NASA's MAVEN spacecraft, which has orbited Mars since September 2014, show that Mars continues to lose atmospheric gases to space today, at rates of about 100 grams per second. Over billions of years, this loss transformed Mars from a world with rivers, lakes, and possibly oceans into the cold, dry desert we see now. The geological record on Mars preserves evidence of this transformation. The Curiosity rover, which landed in Gale Crater in August 2012, found lakebed sediments containing minerals that form in liquid water. The sediments date to about 3.5 billion years ago, showing that Mars had stable liquid water on its surface during the first billion years of its history. The Perseverance rover, landing in Jezero Crater in February 2021, is exploring what appears to be an ancient river delta, with layered sedimentary rocks showing where water once flowed into a crater lake. These discoveries confirm that early Mars had conditions suitable for life, with liquid water persisting for millions of years at minimum. Yet the planet lost this habitability not because its sun brightened too much, but because Mars itself changed. The magnetic field died, the atmosphere eroded, surface water froze or evaporated, and the window for life closed. What makes these case studies particularly revealing is that Venus, Earth, and Mars all started with similar conditions. They formed at approximately the same time, 4.5 to 4.6 billion years ago, from similar materials. All three probably received substantial water from comets and asteroids. All three had volcanic activity releasing gases to form atmospheres. Yet they evolved along dramatically different paths. Venus, too close to the Sun and possibly lacking plate tectonics, became a runaway greenhouse. Mars, too small to maintain interior heat and magnetic field, lost its atmosphere and froze. Earth, through some combination of appropriate distance from the Sun, adequate size to maintain geological activity, and fortunate initial conditions, remained habitable for billions of years. The question is whether Earth's habitability represents typical outcomes for rocky planets, or whether it is anomalous, the result of multiple fortunate circumstances aligning. Statistical analysis of exoplanets discovered over the past 3 decades provides some perspective. The Kepler mission found that planets between 1 and 1.6 times Earth's radius are extremely common, occurring around about 20 to 50% of Sun-like stars, based on extrapolations from Kepler's sample. These planets orbit at various distances, including many in or near their stars' habitable zones. But size alone does not guarantee habitability. A planet could be Earth-sized yet have a thick hydrogen atmosphere like a mini Neptune, or it could be a bare rock with no atmosphere like Mercury, or it could be in runaway greenhouse like Venus. Determining which category a given planet falls into requires measuring atmospheric composition, which is extremely challenging for Earth-sized planets. Recent discoveries have identified several particularly intriguing worlds. In 2015, NASA announced the discovery of Kepler 452b, a planet about 1.6 times Earth's radius, orbiting a Sun-like star every 385 days. The planet sits in the habitable zone, receiving only 10% more stellar radiation than Earth receives from the Sun. The star is about 6 billion years old, 1.5 billion years older than the Sun. If Kepler 452b is indeed Earth-like and started with similar conditions, it might be approaching the end of its habitable period, experiencing the early stages of runaway greenhouse warming as its slightly older star brightens. Unfortunately, Kepler 452b is about 1,400 light-years from Earth, far too distant for atmospheric characterization with current technology. We can only speculate about its current state. Closer to home, the TRAPPIST-1 system, discovered in 2015 and fully characterized in 2017, contains 7 Earth-sized planets orbiting an ultra-cool red dwarf star only 40 light-years from Earth. 3 of these planets orbit in the habitable zone where liquid water could exist. The star is much cooler and dimmer than the Sun, so the habitable zone is very close, with orbital periods of just 6 to 12 days for the habitable zone planets. Red dwarf stars evolve much more slowly than Sun-like stars, so TRAPPIST-1's planets could potentially remain habitable for tens of billions of years if they have atmospheres and geological activity. But red dwarfs are also very active when young, producing powerful flares that could strip away atmospheres. Initial observations with the James Webb Space Telescope in 2023 found no evidence of thick hydrogen atmospheres on TRAPPIST-1b and TRAPPIST-1c, the 2 innermost planets, suggesting they might be rocky. Whether the habitable zone planets have atmospheres remains unknown and is a target for future observations. The statistical distribution of planetary properties remains incomplete because observational biases affect what we can detect. The transit method used by Kepler works best for planets with short orbital periods orbiting close to their stars, making hot planets overrepresented in the sample. Planets in year-long orbits around Sun-like stars are harder to detect because they transit less frequently. Atmospheric characterization is easier for planets orbiting small, dim stars, because the planet's atmosphere blocks a larger fraction of the star's light, making the signal stronger. These biases mean we know more about short-period planets and planets orbiting small stars than about true Earth analogues orbiting Sun-like stars. Correcting for these biases to estimate the true abundance of habitable planets requires sophisticated statistical modeling. One unexplained aspect that keeps appearing across different case studies is the apparent rarity of planets precisely at Earth's size and orbital distance around Sun-like stars. Kepler found that planets come in two main populations. There are rocky planets smaller than about 1.6 Earth radii, and there are mini-Neptunes with thick hydrogen atmospheres between about 2 and 4 Earth radii. There appears to be a gap between these populations, sometimes called the Fulton Gap, after Benjamin Fulton, who identified it in 2017. Earth sits near the upper end of the rocky planet distribution, close to the transition where planets start retaining thick hydrogen atmospheres. This suggests that Earth is near the maximum size for a rocky planet without becoming shrouded in hydrogen. If Earth had been just slightly more massive, it might have retained primordial hydrogen from the solar nebula and become a mini-Neptune, uninhabitable for surface life. The fact that Earth is large enough to maintain geological activity and magnetic field protection, but not so large that it became a mini-Neptune, seems remarkably fortunate. Ongoing research continues to refine our understanding through multiple parallel efforts. NASA's Nancy Grace Roman Space Telescope, scheduled for launch in May 2027, will conduct a census of exoplanets using gravitational microlensing, a technique sensitive to planets at Earth-like distances from their stars. This will provide better statistics on how common true Earth analogues are. The European Space Agency's Ariel mission, planned for 2029, will characterize the atmospheres of about 1,000 exoplanets, mostly hot gas giants and mini-Neptunes. But the data will constrain models of atmospheric evolution that apply to rocky planets as well. Ground-based telescopes like the Extremely Large Telescope, expected to begin operations around 2028, will have the resolution and light-gathering power to directly image some nearby rocky planets and measure their atmospheric compositions. Laboratory experiments complement these observational programs by testing how planetary atmospheres respond to extreme conditions. Researchers at places like the University of Chicago and MIT create high-pressure chambers where they expose gas mixtures to intense ultraviolet radiation, simulating the conditions on planets undergoing runaway greenhouse effects. These experiments measure reaction rates and identify which molecules form under various temperature and pressure conditions. The data feed into atmospheric models, improving predictions of what Venus's atmosphere was like during its transition, or what Earth's atmosphere will be like in hundreds of millions of years. Some experiments focus on cloud formation, trying to understand what controls droplet sizes and cloud lifetime under conditions unlike anything in Earth's current atmosphere. Computer simulations have reached the point where researchers can model entire planetary evolution sequences, from formation through habitability and eventual loss of habitability. These models incorporate stellar evolution, atmospheric chemistry, ocean dynamics, geological processes, and sometimes even simplified biology. Running such models requires enormous computational resources because the timescales span billions of years, while individual processes like weather operate on days. Typically, researchers use simplified parameterizations for fast processes and focus computational effort on the long-term trends. The simulations show that the pathway to habitability loss depends sensitively on initial conditions. Two planets that differ by just 5% in mass or 10% in orbital distance can follow dramatically different evolutionary trajectories. This suggests that habitable planets like Earth might be relatively rare not because the conditions are intrinsically difficult to achieve, but because the parameter space that leads to long-term habitability is narrow. What emerges from comparing Earth to Venus, Mars, and exoplanets is a picture of planetary habitability as a temporary state maintained by delicate balances between stellar evolution, planetary size, orbital distance, atmospheric composition, and geological activity. Earth has maintained these balances for billions of years, but the balance is ending. Venus shows what happens when a planet receives too much stellar radiation or loses its ability to regulate atmospheric carbon dioxide. Mars shows what happens when a planet loses its magnetic field and atmosphere. The exoplanet statistics suggest that many worlds exist in the size and distance ranges that could be habitable, but whether they actually are requires measurements we are only beginning to make. The case studies teach us that habitability is not just about being in the habitable zone. It is about being the right size to maintain geological activity, having the right atmosphere to regulate temperature, having the right orbital distance to receive appropriate radiation as the star evolves, and having all these factors remain favorable for billions of years. Earth has achieved this. The question is how rare that achievement is across the galaxy, and whether intelligent life typically emerges fast enough to... The question is how rare that achievement is across the galaxy, and whether intelligent life typically emerges fast enough to recognize and respond to its planet's finite habitability window. But answering this question faces a profound challenge that goes beyond mere technological limitations. We observe the universe from one location at one moment in cosmic time. Everything we see is filtered through the particular circumstances of our existence here and now. We cannot know with certainty whether Earth's properties are typical or exceptional, because we have only one example of a planet that definitely hosts complex life. This is not just an observational limitation that better telescopes will solve. It is a fundamental constraint on what we can learn about our place in the universe. Our perspective shapes what we can measure, and our measurements might be telling us as much about ourselves as about the cosmos. This problem appears most clearly when considering what astronomers call observational selection effects. We exist on a planet capable of supporting life, which means we automatically exist in the subset of planetary environments where life is possible. This creates a bias in our observations. We cannot observe the universe from a planet where life never arose, because there would be no observers there to make observations. The very fact that we are here to ask questions about habitability means we inhabit a probably unusual location. Most planets are not habitable. Most places in the universe are empty vacuum. The tiny fraction that hosts life, whatever that fraction might be, is special by definition. We live in one of those special places, which means our observations are not representative of typical cosmic conditions. They are representative of conditions where observers can exist. The situation resembles what economists call survivorship bias. During World War II, statistician Abraham Wald studied damage patterns on aircraft returning from combat missions. The planes showed bullet holes concentrated in certain areas like the fuselage and wings, while other areas like the engines showed few hits. The military wanted to add armor to the areas showing the most damage. Wald pointed out that this reasoning was backwards. The planes they were examining had survived. The damage patterns showed where planes could absorb hits and still return. The areas with few bullet holes were actually the vulnerable spots, because planes hit there did not make it back to be measured. The missing data, the planes that crashed, contained the crucial information. Our situation is similar. We can measure the properties of our planet and our evolutionary history, but we cannot measure the properties of planets where life failed to arise or where intelligence never evolved. Those are the missing data points that would tell us whether we are typical or exceptional. How perspective affects what we measure about the universe extends beyond planetary properties to cosmology itself. In 1998, observations of distant supernovae revealed that the universe's expansion is accelerating, driven by what is called dark energy. This discovery, which earned the Nobel Prize in Physics in 2011, fundamentally changed our understanding of cosmic fate. But it also raised uncomfortable questions about cosmic specialness. the density of dark energy appears fine-tuned to allow structure formation in the universe. If dark energy were much stronger, it would have prevented galaxies from forming because space would have expanded too rapidly for gravity to pull matter together. If it were much weaker or negative, the universe might have recollapsed in a big crunch before stars and planets had time to form. The observed value sits in a narrow range that permits complexity. Some physicists argue this is evidence for a multiverse where different regions have different dark energy values, and we necessarily find ourselves in a region where the value permits observers. Others argue it is just coincidence or that we do not yet understand the physics well enough to judge whether the value is truly improbable. This debate echoes an older debate about Earth's position in space. For most of human history, people assumed Earth occupied a special location at the center of the cosmos. Copernicus, in 1543, demonstrated that Earth orbits the Sun, not the other way around. Over subsequent centuries, astronomers found that the Sun is not at the center of the galaxy. The galaxy is not at the center of the universe. And indeed, the universe has no center at all. This sequence of discoveries is sometimes called the Copernican principle, or the principle of mediocrity. It states that we should not assume we occupy a special location without strong evidence. Applied to modern cosmology, the principle suggests that our location in the universe should be typical of places where observers can exist. We should not find ourselves in an exceptionally rare environment unless being in such an environment is necessary for observers to exist. But Earth arguably does occupy an exceptional position in at least some respects. The planet sits in the habitable zone, which already makes it unusual compared to most planets. It has a large moon that stabilizes the axial tilt and drives tides, potentially important for life's development. It has plate tectonics, which might be rare among rocky planets. It has a magnetic field protecting the atmosphere. Jupiter's gravity may have reduced the rate of asteroid impacts on Earth by deflecting many asteroids before they reached the inner solar system, though this effect's importance is debated. Any one of these properties might be common, but having all of them simultaneously could be rare. If long-term habitability requires this particular combination of features, then Earth might be anomalous among planets in ways that matter for life's emergence and persistence. The concept of living in a bubble, a region of space or time that is not representative of broader conditions, appears in multiple contexts. On cosmic scales, there is the possibility that our observable universe is not typical of the universe as a whole. If the universe is vastly larger than the part we can see. Extending far beyond our cosmic horizon, different regions might have different physical properties. Inflation theory, which describes rapid expansion in the universe's first fraction of a second, predicts that different regions could inflate by different amounts, creating pocket universes with different physical constants or even different physical laws. If true, we inhabit whichever pocket universe has properties compatible with life. This is an extreme form of selection bias. We see the physics we see not because it is fundamental, but because it is compatible with our existence. Other physics might exist in other regions, but we cannot observe those regions, and even if we could, we would not exist there to do the observing. On galactic scales, the question is whether the solar system's location in the Milky Way is typical or special. The Sun orbits about 26,000 light-years from the galactic center, placing it in the galactic disk, but well away from the dense central regions. Some researchers have proposed that this location is unusually favorable for life, because it is neither too close to the galactic center, where supernova rates and radiation levels are high, nor too far out, where heavy element abundances are low. This idea, sometimes called the galactic habitable zone hypothesis, suggests that most stars suitable for hosting life-bearing planets occupy an annular region at intermediate distances from their galactic centers. Critics point out that life's requirements are not well enough understood to confidently delineate galactic habitable zones, and that planets might be hardy enough to survive in a wider range of galactic environments than initially assumed. The debate remains unresolved. The typicality versus specialness question has implications for the search for extraterrestrial intelligence. If Earth is typical and intelligence commonly emerges on habitable planets, then we might expect to find evidence of other civilizations, either through radio signals, visible signatures like Dyson spheres capturing stellar energy, or artifacts left behind in the solar system. The fact that we see no such evidence despite decades of searching constitutes the Fermi paradox. Various solutions have been proposed. Perhaps intelligence is rare because it requires many improbable evolutionary steps. Perhaps civilizations self-destruct before reaching the stage where they become detectable across interstellar distances. Perhaps they exist, but deliberately avoid making themselves conspicuous. Perhaps they exist, but use communication methods we have not thought to look for. Or perhaps Earth is genuinely unusual, and planets with billion-year scale habitability suitable for evolving complex life are rare enough that few exist within our observable region of the galaxy. Anthropic reasoning, the practice of using the fact of our existence as data in scientific arguments, is controversial because it can lead to circular logic if applied carelessly. The strong anthropic principle says we should not be surprised to measure conditions compatible with our existence, because we could not exist to measure anything else. This is trivially true, but scientifically vacuous. It does not predict anything or rule anything out. The weak anthropic principle is more useful. It says that among the range of possible environmental conditions in the universe, observations made by intelligent observers will be biased toward conditions that permit intelligent observers. This can make predictions. For instance, if we want to estimate how common life is in the universe, we should not just count the fraction of planets that are habitable. We should also weight this by the probability that observers actually arise in habitable environments and persist long enough to develop technology capable of astronomy. Our existence provides information about this weighted probability, though extracting that information requires careful reasoning. Future surveys will dramatically expand the sample of known planets and potentially find other worlds similar to Earth. The European Space Agency's Plato mission will survey 1 million stars looking for transiting planets, with a focus on finding Earth-sized planets in Earth-like orbits around Sun-like stars. Measuring hundreds or thousands of such planets and determining what fractions show signs of atmospheres, water vapor, oxygen, or other biosignatures would begin to answer whether Earth is typical. If most Earth-like planets appear habitable, it suggests Earth is not special. If most appear to be in runaway greenhouse states like Venus or frozen like Mars, it suggests habitability is fragile and Earth might be fortunate. Even finding no biosignatures would be informative. It would suggest either that life is rare, or that biosignatures are difficult to detect, or that we are searching in the wrong ways. The use of Earth and the solar system as a natural laboratory for understanding planetary evolution is one of the most powerful tools available to planetary science. We can study Venus to see what runaway greenhouse effects look like. We can study Mars to understand atmospheric loss and interior cooling. We can study Jupiter's moon, Europa, and Saturn's moon, Enceladus, to probe habitability in ocean worlds. We can study Saturn's moon Titan to examine complex organic chemistry in a thick nitrogen atmosphere. Each world provides data about different pathways of planetary evolution under different conditions. By understanding the full diversity of outcomes in our solar system, we can train models that we then apply to exoplanets. The solar system is not a random sample of all possible planetary systems, but it is the only system where we can send spacecraft to make detailed in situ measurements. Every rock sample returned from Mars, every measurement made by a probe descending through Titan's atmosphere, every spectrum of Europa's surface adds data that refines our understanding of planetary processes. The stakes in this debate about typicality extend to how we think about humanity's cosmic significance. If Earth is typical and we exist at a typical time in our planet's habitable history, then our situation is unremarkable. Life probably arose on many planets. Intelligence probably emerged in many places. The universe might be filled with civilizations at various stages of development. Our eventual extinction when Earth becomes uninhabitable would be sad for us, but cosmically ordinary. But if Earth is unusual, if the combination of properties that permitted complex life to persist for billions of years is rare, then we might be among the first, or perhaps the only intelligence to arise in our region of the galaxy. In this scenario, our extinction would be cosmically significant because it might mean the extinction of the only observers capable of understanding the universe in this entire galactic neighborhood. The universe would continue, but it would continue without anyone nearby to witness it or comprehend it. This returns to questions philosophers have debated for centuries about whether the universe requires observers to have meaning, or whether it is indifferent to whether anyone is watching. From a physical standpoint, the universe operates according to laws that do not care about observation. Stars fuse hydrogen whether anyone measures the process or not. But from an epistemological standpoint, a universe with no observers is a universe about which nothing can be known. Knowledge requires knowers. In this sense, the emergence of intelligence transforms the universe from a collection of processes into something that can be understood. When Earth's habitability ends and intelligence disappears, if it is not preserved elsewhere, something profound is lost. Not the physical universe, which continues, but the understanding of that universe, the ability to ask questions about it, the capacity to measure and model and marvel at it. The observational biases that constrain what we can know are not mere technical problems to be solved with better instruments. They are fundamental features of how knowledge works for located, embodied observers inhabiting a particular place and time. We cannot step outside our perspective to view the universe objectively from nowhere. We can only work to understand our biases, account for them in our reasoning, and construct models that acknowledge the limits of what we can measure. The fact that we exist at this particular moment on this particular planet during this narrow window when complex life and intelligence are possible shapes everything we know and everything we can know. We are not separate from the universe observing it from outside. We are part of the universe observing itself, and that we are part of the universe observing itself, and that participation is temporary. The timeline for Earthsary, the timeline for Earth's habitability extends perhaps 1 billion more years if we are optimistic, 500 million if we are pessimistic. Beyond that window, the planet transitions to a state incompatible with complex life. The sun continues brightening at its steady, predictable rate of 1% per 100 million years. The mechanisms are understood, the outcome is certain. What remains uncertain is what, if anything, humanity becomes during the time available, and whether anything we would recognize as our legacy persists beyond Earth's habitability window. The long-term evolution of the sun follows a path that has been calculated in extraordinary detail through stellar evolution models refined over decades. For the next 5 billion years, the Sun will remain on the main sequence, steadily converting hydrogen to helium in its core. The core temperature will gradually increase as the helium accumulates, and gravity compresses the core more tightly. The fusion rate will increase correspondingly. The Sun's luminosity will reach approximately twice its current value in about 5 billion years, just before the core hydrogen is finally exhausted. At that point, the Sun transitions off the main sequence into the subgiant phase. The core, now composed almost entirely of helium, contracts rapidly under its own gravity. This contraction releases gravitational energy and heats the surrounding shell of hydrogen. The temperature in this shell rises high enough to ignite hydrogen fusion in a spherical shell around the inert helium core. This shell burning produces more energy than the core burning did during the main sequence phase. The extra energy causes the Sun's outer layers to expand dramatically. Over a period of about 1 billion years, the Sun grows into a red giant with a radius approximately 100 to 200 times its current size. The exact final radius remains somewhat uncertain, depending on details of mass loss and atmospheric dynamics, but all models agree the expansion is enormous. The Sun's surface temperature drops to about 3,000 Kelvin as the energy is spread over a vastly larger surface area, which gives the star its red color. Despite the cooler surface, the total energy output increases significantly because of the much larger radiating area. At its maximum extent, the red giant Sun will be luminous enough to be visible from Earth's orbit, if Earth still exists, as an object filling roughly 1/3 of the sky. Earth's orbit during this phase depends critically on how much mass the Sun loses. As the Sun expands into a red giant, its loosely bound outer layers are gradually blown away by stellar winds and radiation pressure. Models suggest the Sun will lose approximately 30 to 50% of its mass during the red giant and subsequent asymptotic giant branch phases. As the Sun loses mass, its gravitational pull on the planets weakens. This causes planetary orbits to spiral outward, following conservation of angular momentum. The question is whether Earth spirals outward fast enough to avoid being engulfed by the expanding stellar envelope. Calculations by Schroeder and Smith in 2001 suggested that Earth likely gets engulfed, but the uncertainties are large enough that survival as a scorched remnant remains possible. Either way, Earth will have been uninhabitable for billions of years before this final act. The oceans will have boiled away 3 to 4 billion years earlier, when the runaway greenhouse began. The atmosphere will have been stripped by solar wind after losing its protective magnetic field. What might be engulfed is merely a rocky corpse, all traces of biology long since erased. After reaching maximum size, the red giant Sun will pulsate, expanding and contracting over periods of months to years. These pulsations drive powerful stellar winds that blow away more of the outer envelope. Eventually, the Sun ejects most of its remaining outer layers in one or more shells of gas that expand outward into space. These shells form a planetary nebula, one of the most beautiful types of objects in astronomy. The name is misleading. Planetary nebulae have nothing to do with planets, but were named by early observers who thought they looked like planetary disks through small telescopes. A planetary nebula is simply the outer atmosphere of a dying star, cast off and illuminated by ultraviolet radiation from the exposed core. The shells glow with characteristic colors from excited atoms, oxygen producing green light, hydrogen producing red, nitrogen producing red and violet. The nebula expands at speeds of tens of kilometers per second and remains visible for tens of thousands of years before dispersing into the interstellar medium. What remains at the center after the nebula disperses is a white dwarf, the exposed helium core of the original star. White dwarfs are extraordinarily dense objects, packing roughly half the Sun's mass into a sphere about the size of Earth. A teaspoon of white dwarf material would weigh several tons at Earth's surface. The density is so extreme that the matter exists in a degenerate state, where quantum mechanical effects prevent further compression. Electrons cannot occupy the same quantum state, which creates a pressure that supports the white dwarf against gravitational collapse. This degeneracy pressure is independent of temperature, which means the white dwarf needs no ongoing fusion to support itself. It is essentially a slowly cooling ember, radiating away its residual heat over trillions of years. The white dwarf sun will have a surface temperature initially around 100,000 Kelvin, hot enough to emit primarily in ultraviolet wavelengths. Over millions of years, it cools to tens of thousands of Kelvin, entering the visible spectrum and appearing as a brilliant blue-white star despite being much fainter than the original Sun. If any planets survive in the outer solar system, they will experience bizarre conditions. The white dwarf provides little warmth, but its intense ultraviolet radiation could strip atmospheres from anything nearby. Jupiter's moons, which might have become habitable during the red giant phase as temperatures in the outer solar system soared, would freeze again as the white dwarf cools. The window for habitability in the outer solar system, if it ever opens, would close again within tens of millions of years after the planetary nebula phase. Over billions of years, the white dwarf continues cooling. It transitions from blue-white to yellow to red as its surface temperature drops. Eventually, after perhaps 10 to 15 billion years, it becomes too cool to emit visible light at all. It becomes a black dwarf, a dark sphere of degenerate matter drifting through space, radiating only in the infrared and barely detectable. The timescale for this cooling is longer than the current age of the universe. No black dwarfs yet exist anywhere in the cosmos because the universe is only 13.8 billion years old. The oldest white dwarfs, which formed from the first generation of stars to die, are still glowing faintly. But in the far future, as the universe ages, white dwarfs will dominate the stellar census. Most stars end their lives as white dwarfs. Most of the matter that was once in stars will eventually be locked in these cooling relics. The implications for life and civilization across these timescales are profound and strange. If humanity or its descendants persist for even 1 million years, vastly longer than our history so far, they would witness minimal changes in the Sun or Earth. The Sun would be perhaps 1% brighter. Climate changes would be detectable but modest. Earth would still be habitable, though warming trends might be accelerating. A civilization lasting 10 million years would see the Sun brighten about 10%. The effects would be more significant. Ice sheets would be smaller, sea levels would be higher. Climate zones would be shifting, but adaptation would be possible through technology or biological evolution or both. A civilization lasting 100 million years would see the Sun brighten enough to make current climate zones uninhabitable. Equatorial regions might become too hot for human-like biology. High latitudes would be more temperate. The carbonate-silicate cycle would be working harder to draw down atmospheric carbon dioxide to compensate for increasing solar radiation. Life would be stressed, but not yet at crisis point. But no biological species lasting 100 million years would resemble its ancestors. Humans have existed for 300,000 years. In 100 million years, evolution would produce something utterly different, assuming natural selection continues to operate. More likely, any technological civilization persisting that long would have long since transcended biological evolution through technological means. The distinction between biological and artificial, between evolved and engineered, would have blurred beyond recognition. What matters for such timescales is not the survival of Homo sapiens specifically, but the continuation of some lineage that traces its origin to Earth and inherits some fragment of human knowledge, values, or purpose. Whether that continuation happens through biological descendants, artificial intelligences, or hybrid forms we cannot yet imagine is an open question. The probability that any such lineage remains on Earth throughout its habitability window is essentially zero. Any civilization capable of surviving hundreds of millions of years will necessarily have expanded beyond a single planet, likely beyond a single star system. The motivations are simple. Earth's habitability is finite. Remaining exclusively on Earth means accepting extinction when habitability ends. But spreading to other worlds faces enormous challenges. Interstellar distances are vast. The nearest star system, Alpha Centauri, is 4.3 light-years away. With current propulsion technology, reaching it would take tens of thousands of years. Even with advanced propulsion reaching significant fractions of light speed, the journey would take decades to centuries. Establishing self-sufficient colonies on other worlds requires transporting enormous resources or developing the capability to utilize local materials. The energy requirements are staggering. Yet if civilizations commonly last millions of years, they have time to solve these problems. The technical challenges of interstellar travel are not violations of physical law, merely engineering difficulties that require enormous energy and resources. A civilization with millions of years and exponentially growing knowledge might develop techniques we cannot currently envision, perhaps exploiting quantum phenomena or space-time geometry in ways our current physics does not suggest. Or they might pursue slower but more certain strategies, sending generation ships or frozen colonists, or even just encoded information that could reconstitute life and civilization at the destination. Over millions of years, even slow expansion at sublight speeds could reach thousands of nearby stars. The galaxy itself is only about 100,000 light-years across. A civilization expanding at just 1% of light speed could, in principle, reach the entire galaxy in about 10 million years, faster than the timescale on which Earth's habitability degrades. This raises the question of why we see no evidence of such expansion by others. The Milky Way is about 10 billion years old. Stars have been forming and dying for all that time. Earth and the Sun are relative latecomers, forming only 4.6 billion years ago. Many stars are billions of years older. If civilizations commonly arise and commonly expand across the galaxy, we should see evidence of this expansion. We should detect megastructures, artificial signals, modified stars, something indicating intelligence has been here. The fact that we see none of this suggests either that civilizations are rare, or that they do not expand, or that they expand in ways that leave no detectable traces, or that they have been here but we have not yet recognized the evidence. Each possibility has implications for how we think about humanity's future and our ultimate fate. Other observers might already be contemplating the same questions we face, watching their own stars brighten, calculating their own deadlines, deciding whether to flee or adapt or simply accept extinction when their time comes. If intelligence is common, the galaxy might contain thousands or millions of species, each facing the same fundamental constraint that their homeworlds are temporary. Some might have already gone extinct when their planets became uninhabitable. Some might be in the process of spreading to other worlds, engaged in the slow work of interstellar colonization. Some might be millions or billions of years ahead of us, having long since solved problems we are only beginning to confront. But they are silent or distant or unrecognizable to our searches. We remain alone in our observations, which leaves us uncertain whether our situation is common or rare, whether our future is typical or exceptional. And yet, the basic conclusion seems inescapable regardless of these uncertainties. The sun will swallow Earth in 5 billion years, but humanity is already gone, not because we destroy ourselves or because some external catastrophe strikes, but because 5 billion years is incomprehensibly long. Nothing recognizable as human could persist across such a span. Even 1 billion years is impossibly long. Even 100 million years transforms everything beyond recognition. The people reading these words now will be dead in decades. Their descendants will be different people with different concerns. Their descendants' across millions of generations will be so changed by evolution, technology, and adaptation to new environments that calling them human would be purely symbolic, a courtesy extended to acknowledge shared ancestry rather than shared form or nature. By the time the sun expands into a red giant, everything we are, everything we think defines humanity, will have been transformed, destroyed, or forgotten so long ago that the connection will be unrecognizable. We are already gone in the sense that our particular moment, our particular way of being, cannot persist. The universe continues, but we do not continue with it, not as we are. This realization is not depressing if you sit with it long enough. It is simply true. Everything is temporary. Species go extinct. Civilizations fall. Planets become uninhabitable. Stars die. Even galaxies will eventually exhaust their gas and stop forming new stars, leaving only slowly cooling remnants. The universe trends toward equilibrium, toward maximum entropy, toward silence. But knowing this does not diminish the meaning of what happens now. If anything, the temporary nature of existence makes the present more precious. We are here now, brief sparks of consciousness during one narrow window when conditions permit complexity and thought. We can measure the cosmos, understand our place in it, feel wonder at its vastness and our smallness within it. The fact that this capacity is temporary does not make it less real or less valuable. It is all the more valuable for being fleeting. So as you drift towards sleep tonight, consider that you exist at this peculiar moment when Earth is habitable, when the sun shines steadily, when humanity is poised between its past as terrestrial organisms and its potential future among the stars. You are here during the narrow window when complex life is possible, when intelligence has emerged but before the deadline closes in. Whatever happens across the eons beyond your lifetime, whether humanity spreads across the galaxy or fades quietly into extinction, whether other civilizations exist or we are alone, this moment is real. You are part of the universe becoming aware of itself, briefly, imperfectly, but genuinely. The sun will continue burning for billions of years, brightening slowly, eventually expanding to consume the worlds that orbit it now. But that is the sun's story, not yours. Your story happens here, now, during this brief interval of warmth and stability and breathable air. If this journey through deep time and stellar death spoke to you, consider subscribing to find more explorations of cosmic mysteries that help you drift off into contemplation. There are more questions waiting, more timescales to examine, more perspectives to adopt on our temporary existence in this vast, evolving universe. Leave a like if you found peace in accepting impermanence, in recognizing that endings are built into the structure of everything, that the sun's slow brightening toward our planet's eventual sterilization is not malice, but simply physics. And good night, wherever you are in this universe that will outlast us all, under stars that are themselves temporary, in a cosmos that permits brief windows of complexity and consciousness. before returning everything to simplicity and silence.